everyone, welcome back to my YouTube channel. I am Reeti and I am back with another lecture in the DBMS series. So without any further ado, let's get started. So what is intention? Intention defines what kind of data can be stored, basically the data type and the relationships between them. So whenever we discuss about what kind of data that can be stored in a table and what kind of relationships table can have in between them, that is called as intention. Now this is basically the blueprint or the definition of the database structure. So basically in the definition of database, we mostly tell that what kind of tables would be there, what would be the data which would be present in the tables, basically the data type, the constraints the table would be having. So it basically tells us about the database structure. Now it doesn't change frequently and it's permanent definition of the database structure. So it doesn't change frequently because consider that if we have a huge database of employee. Now in this employee database, we might be having a employee details table, and one about employee previous work history table. So employee work history table. Now in these certain tables, there is like very less addition of new columns, or you can say new set of attributes which are being introduced. So there is not a kind of permanent change which happens very frequently. So that is why it is told that it is a permanent definition, because the changes are not very frequent. Yeah, maybe there could be a possibility of adding one more or two more new attributes or column, but that doesn't occur very frequently. It's very rare. So that is why it is called as the permanent definition of database structure. Now it includes the very first thing, table definition. So what table definition is? Basically the name of tables, their columns and the data type allowed in each column. So in a database, you can have multiple tables. What is database? Database is basically collection of data. And tables is basically an intersection of attributes and tuples, or you can say rows and columns. So here there could be multiple table T1 and T2. So what is this particular table name, along with what all are the data types of the data which is being stored, then what are the constraints which are provided to this particular data, that all things we discuss in intention. Now the second thing is constraints. So constraints are basically the rules that governs the data, such as primary key, foreign key and data validation rules. So constraints basically allows that if this particular data is being stored, does it follow this particular rule of a primary key constraint? Does the column shouldn't hold any duplicate values because it is having a primary key constraint. If it is having a not null constraint, it shouldn't take any null values. So that type of validation rules are performed. Now the third one is relationship between the tables. So there could be a relationship between the table, like foreign key primary key relationship, wherein one table is having a shared column with another table. There is one foreign key which is present in one table and there is one primary key which is being referenced by that foreign key in another table. So there is also a relationship which is established between two tables of databases. Now here is an example. So here we have taken an example of a customer table. So this is the table name. These are the table attributes, or you can say column, table columns. These are the data types of the attributes or the table columns, so you can say data types. So this proves our first point, that it includes the table definition, that is name of table, their column and data types allowed. Now the second thing which you can see here is a constraint, which is a primary key constraint. There is a rule on this ID column that ID should always hold unique as well as not null values. It can't hold any duplicated values because of this primary key constraint. So it also proves our second point, that is it includes constraint. Now the third one is relationship between tables. Since here we are discussing only about one table, we don't know that if there are more tables in the database which is existing. So for now I haven't given any foreign key or primary key relationship, but consider that if there are two tables, there could be a possibility that a primary key in first table can be acting as a foreign key in second table, establishing a foreign key primary key relationship between the tables. So in this way a relationship is also defined. So intention basically consists of table name, the constraint it has, the data type it has, the column name it has, basically the structure of the database or the structure of the tables which is present inside our database. It is the intention in database. So let's see what is extension in database. The extension is the actual data that is stored in database at a given instance in time. So whenever we see the actual data which is stored in database at a given time, that is called as extension. Basically the data which is stored in tuple or rows at a given instance of time. When there are more tuples added, the data can change. So consider that at a time t1, I am looking at my employee table. In this employee table, I can see there is ID, name and department. And there are entry of 3 people, Rahul, Afsara and Abhimanyu. Now company hire new individual. So whenever they will hire new individual, the tuple or the row would be filled with new values. Now if I see my table at time T2, I can see that there are 4 entries in my table now. So our entry for Aditya is newly added at time T2. So at time T1 I was seeing then there were only 3 people. Consider after 5 days if I am seeing, I can see that there are 4 people now in that particular employee table. Consider that after 10 days if I am seeing the table, I can see that there are 5 entries in the table. So Raj is also added newly. So at particular instance of time, the data which is present in the database is called as extension in database. So extension in database is not permanent because there would be more number of employees who would be added. There would be some employees who would be also leaving the company. So the extension doesn't remains permanent, but intention is kind of permanent because in that we basically define the table structure or the table definition. So extension is basically the actual data which is stored at a given instance in time. Intention is the table structure, or you can say table blueprint. Now before learning about RDBMS, let's learn about database and database management system. So what is database? Database is basically collection of data. So whenever we have a collection of data, we call it as database. Now what is this database management system? It is a software application to manage our data, or you can say to perform CRUD operations on our data. Now consider that we have a lot of data in our database. Now we need to manage that data. Basically, whenever we want to do some creation in the data, some updation in the data, some insertion in the data, or some deletion in the data. So for managing all those CRUD operations, we need a software which will help me to manage my data which is present in the database. So that is DBMS. Consider that there is a user. Now user wants to manage a database. So it will use a software application to manage that database, and that particular software application is called as DBMS. Now databases are of 2 types. First is relational database and second is non-relational database. Now what are the differences between them? So relational databases basically use table to store data. So whenever we are using tables to store our data in databases, we call it as relational databases. The example are MySQL, Oracle and MariaDB. Now what is non-relational databases? So whenever the data is not stored in tables, we call it as non-relational databases. The example is MongoDB. So they could be stored in key value pair or some different thing, but they are not stored in the form of tables. So relational databases are the database which is stored in the form of tables. Non-relational databases are the database which basically follow some other pattern like key value pair or some other pattern to store the data. So just now we learnt about relational databases. Now what is a database? Database is basically a collection of data. In that particular database, there could be multiple tables, T1, T2. What is relational database? Relational database is a database in which data is stored in the form of tables. Also the tables which is present inside the database can have a relationship between them. So that is why it is called as relational, because the tables inside the database can establish a relationship between them. So this is relational databases. Now to perform CRUD operations or to manage data of the relational database, we need a software. So that software is called as relational database management system. So whenever we use a software to manage data of relational databases, we use this relational database management system. So these database structure data into organized table that have some predefined connections or relationships between them. Data manipulation and querying are performed using SQL. So we use SQL, that is structured query language, to perform any kind of data manipulation or query in our data which is present in our database. So we use this as a programming language to perform any kind of CRUD operation. So here if you see, there is a user. Now user is using a software application. So in terms of relational databases, we use RDBMS. Now an example of RDBMS is MySQL. So basically MySQL is a software which helps us to perform the CRUD operations, and SQL is the programming language which we use to do some manipulation or querying in the data. So MySQL is the RDBMS and SQL is the programming language which we use to perform the queries. Now this is the database on which we perform the query. So this was all about relational database management system. In one word, relational database management system are the softwares which help us to manage the data which is present in relational databases. Now in relational database, data are stored in the form of tables and they have some connections or relationships between them. So now Normalization is quite important in terms of semester exams, but it is also asked in interviews as well, like tell about normalization, what are the types of normalization, what is denormalization. So this is an important topic, so don't skip this video. Always have a clarity about what normalization is, what are the types of normalization in terms of interview point of view. So let's understand about normalization. Now, normalization is a process in which we organize the data to reduce redundancy, that is duplicacy of data, and improve the data consistency, that is same set of data is present across each databases. So it involves dividing a database into two or more tables. Now what is normalization? Consider that there is a table of employee which is having employee details such as employee ID, employee name, employee department name, employee department ID, and employee department phone number. Now there is a table of employee which is having all the details such as ID, name, department ID, and department phone number. Consider you enter the details of first employee. So employee ID is 1, name is Riti, department name is IT, department ID is 01, and department phone number is considered +91 something. Now again you are asked to insert details of second employee who is in the same department. So you go ahead and insert the detail of the second employee. So here employee ID would be 2, the name would be considered Raj, the department name is IT, the department ID is again 01, and the department phone number is the same which is given above. Now here can you see that this department name, department ID, and department phone number is something whenever we insert any details of the employee who is in IT department is getting repeated. So here also we are repeating IT, department ID, department name. Here also we are doing the same thing. Consider that there are bunch of employees who are in IT department. So we have to do this repetition each and every time whenever we are inserting any of the employee details who is working in IT department. So what happens here is now, consider that if you want to update something, that the department ID is considered now 02. So you have to go ahead and update for each and every employee separately. So it is kind of increasing the duplicacy in the database because same set of data is getting inserted each and every time and it is a duplicate data. So what we do here is we introduce a concept of normalization which says that if you are facing any duplicacy of data or any inconsistency of data. So what is data consistency and how this data can be inconsistent? Consider that the department ID is 02 now for IT. So you updated it here, you updated it here. Consider that there are n number of employees who are working in IT department. And if you miss out to update for any one of the employee, it will show the department ID as 01 for that employee, but that employee is working in IT department. So that would be an inconsistent or you can say incorrect data. So that is why we can see that whenever we make a table which is having like details of employee ID, employee department details as well, we can see that there is a data duplicacy as well as data inconsistency or the data consistency is very less. So because of that, we introduce the concept of normalization. Now, what is data redundancy and consistency and why it's important? So whenever there is a same set of data repeated at each and every time, it results in the duplicacy of data. That is the same set of data IT01 which is getting repeated each and every time. So which is resulting in the duplicacy of data. Now row level duplicacy can be removed by using primary key for unique values. Now there are two types of duplicacy which happens. One is column level and one is row level. So here you can see that for certain columns, department name, department ID and department phone number, these all values are getting repeated for some certain number of columns. So this is called as column level duplicacy. Now coming to row level duplicacy. So in row level duplicacy, what happens? Consider that there is ID and there is employee name. So here you give the ID as 1, the name as consider Riti. Again you are giving the ID as 1 and the name as Raj. Again you are giving ID as 1 and name as Rahul. Like For employee it won't happen, but consider for school database or for college database, there could be a possibility that there are two people who are having the same name. So how you are going to differentiate between that two people? Because again, ID is something on basis of which we are differentiating the name. So if I am giving roll number 1 to Rahul Kumar and roll number 1 to Rahul Raj as well, so how I'll differentiate that which Rahul is this, Rahul Kumar or Rahul Raj? So that is why we introduce the concept of primary key. We will make sure that all the values which is present in the ID column, if we are making it a primary key, is unique as well as not null. So whenever we make sure that this is unique and not null, what will happen that the ID is 1 for Riti. Now the ID can be anything apart from 1 for Raj, and ID can be anything apart from 1 for Rahul. So this particular thing is now sorted because now we are getting unique values, and in terms of ID I can find that which person is this. Like if I say that ID is 2, I can surely say that this is Raj. If I say ID is 3, I can surely say that this is Rahul. So basically on basis of ID, we are somehow eliminating the duplicacy which was happening in each and every record for ID being 1. So in this way, we remove the row level duplicacy. But whenever we are encountering any column level duplicacy, for that we take the help of normalization. Now, whenever we have some data or some set of columns, it leads to different anomalies, or you can say inconsistency or error that occurs when manipulating or querying the data in the database. So as I told, consider that if you want to update department ID, so maybe you updated for each and every value, but some of the values were left. So there is a data inconsistency. Consider what happens is there is a new set of employees who come to our company and all these employees have left. So if I delete the data of Riti and Raj, we will lose the details of the department name, department ID and department phone number, because I don't have any separate table where I have all the details, like if it is a IT department, what is the department ID and what is the department name. And consider that if I want to somehow insert some data, then again it will be same duplicacy which will happen for each and every employee for whom I am inserting the data. Like the same thing, IT01 and phone number would be repeating for them. So that leads to anomalies. Now what are the anomalies? First is the insertion anomaly, second is the updation anomaly, and third is the deletion anomaly. Also, it increases the size of database with the same data. Now again, the same set of data is getting repeated each and every time. So it is increasing the size of database, because every time I have to give IT, department name and department phone number each and every time. So somehow it's increasing the size of our database. It's increasing the data duplicacy, or you can say the redundancy. It is causing data inconsistency as well. Now these are the anomalies which happen whenever we have some redundant, or you can say duplicate data and inconsistent data. Now let's learn about each and every anomaly and understand that how this anomaly occurs. So let's learn about very first of the anomaly, that is insertion anomaly. It occurs when it is difficult to insert data into the database due to absence of other required data. Now what does this mean? Consider a very lame example that there is a student who took an admission in a particular school. Now student is going to take admission in class 6, but right now he doesn't know that he is going to be in class 6A, 6B, 6C. Like in which section student is going to get admitted, he doesn't know. He only knows that he is taking admission in class 6. Now in 6A there are different set of teachers who are teaching. In 6B also there are different set of teachers. In 6C also there are different set of teachers. Now again, this particular student doesn't know that which particular teacher would be teaching him or her. And again, the class teacher would also be different for each of the sections. So all these details the student who has just taken an admission doesn't know. But we want to insert the detail of the student in our student database. So for all these fields, like what is the section, what is the teacher name, what is the class teacher name, we have to keep it as empty or null, because right now we don't know that what are the values or who are the person who is going to teach, what is the section in which student would be admitting in. So here also I have taken an example that consider you want to add a new department, but there is no employee in the department yet. So consider that in our company, there is a new department which is being introduced. There is IT and HR department, but now there is a supply chain department. Now for the supply chain department, this is a very new department which is being introduced. So I know the manager name of this particular department, I know the salary of this particular department, but as of now there is no employee who is working in this particular department. So I have to keep all these values as null, and I have to only insert the department values, because right now in this particular table we are having all the details of the department as well as all the details of employees. But right now, since this is a very new department, none of the employee is assigned to this particular department. So for now, these all values would be null. So this is called as insertion anomaly, when it is difficult to insert data into the database due to absence of other required data. Because consider that if ID is a primary key, I can't keep ID as null, right? Primary key, what it says is, if an attribute or a set of attributes is declared as primary key, it will always be unique as well as not null. But here we have to insert null value, because right now in supply chain department there is no employee who is existing. So it will violate the rule of primary key. That is why an insertion anomaly is caused whenever we have a big, or you can say huge, database where we are storing the details of each and everything. Now the second is deletion anomaly. Now it occurs when we delete data, it removes the other valuable data. So consider that if we are deleting the data of any of the employee, it removes the other valuable data which we need for new set of employees who are joining the company. So consider that right now all the employees have left the company. So what it will do is, it will delete the entire data which is present for all the employees. Now it has deleted the entire data. But wait a second, while deleting the entire data, we are somehow losing the data of department, manager and salary, because we have deleted all the data which was present in our table. Now we don't know that what is the department, what is the manager of that particular department, and what is the salary, because we don't have any other table where we have the details of department, the manager who is of that particular department, and the salary details. So somehow while deleting the data which is present in the table, we are losing the set of valuable data which we require. Because consider that there is a new employee who has just joined the company. Now for that particular employee, I know the name, age and department, but I don't know the details of manager and salary, because it was present for the earlier employees. But for that particular employees, I have already deleted the data which was present. So I won't be knowing that if the person has joined the HR department, who is the manager and who is the salary. So whenever we delete data, it removes the other valuable data. So consider if you delete all the record in the table, you will lose the track of department, their manager and salaries. Now the third anomaly is updation anomaly. It occurs when changes to data require multiple updates. So whenever we are changing any set of data and it requires multiple updates to be done, because that particular data is present at multiple places. So whenever we are changing any data that require multiple updates, then the updation anomaly happens. Consider you want to change the salary for people who are working in HR department. You need to update it at 3 places. So here you can see that there are 3 people who are working in the HR department, and for now the people who are working in HR department have got an increment, and now their salary is been increased to 1200. Now we want to update at all the places where the HR department is present with this salary. But right now we are only dealing with data of 5 employees. But in general or in real life scenario, there are always a bunch of employees who work in a company. So whenever you want to update the salary of employees who are working in HR department, it will require a lot of effort, because that particular data would be present for lot of employees who are working. And consider that by any chance you miss to update salary of one of the employees, so it will show incorrect data, that is data inconsistency would be there. So it leads to updation anomaly. Basically we have to do multiple updates of the data where the data is getting changed. So that is why updation anomaly happens. So how normalization help us here? Using normalization, we can divide the employee table into 2 tables. First table is employee table and the second table is department table. So let's see from here. Here you can see that department, manager and salary is something which is getting repeated for each and every employee. So what we did was we broke the table into 2 sub tables. So the first table would be having details such as employee ID, employee name, age and department. And the second table would be having details such as employee department, employee manager and employee salary. So let's see. So here we are having 2 tables, employee table and department table, wherein employee table is having details such as employee ID, name, age, and department. And now from this we can identify that which department the employee is, and from the department table we can fetch in the details such as department name, department manager, and department salary. So we have broke the table into two parts so that we can reduce the redundancy or data inconsistency which is being occurred. Now the first question which would be coming to your mind is, here also in the department column we are seeing duplicacy. The IT department is getting duplicated 2 times, the HR department is getting duplicated 3 times. Now normalization doesn't guarantee you to remove the entire duplicacy or entire data redundancy. What it says is it will lower down or it will reduce the data redundancy or duplicacy which is present in the table. So normalization doesn't guarantee you to remove the entire duplicacy, but it guarantees you to reduce the duplicacy or the redundancy which we have. Now here you can see that the duplicacy is being reduced because now I just need to provide a department name for any of the person who is joining my company. So let's see about all the 3 anomalies we discussed, how normalization is helping us to reduce the insertion anomaly, deletion anomaly, and updation anomaly. Now consider that if there is a new employee who joined my company, so I can fill in the details of employee ID, employee name, employee age, and for now I can keep the department as null, and whenever the employee is assigned any department, all the department details is present here. So there is no duplicacy which is present for the employee, there is no null values which are being given to the primary key which is present here. We are only giving the department as null because right now I don't know which department the employee belongs to, but whenever the employee is assigned a department, I'll just fill in the department details, and from this particular table I'll get all the details of the department in which the new employee would be working. So insertion anomaly is reduced here. Now coming to the deletion anomaly, consider that you are deleting all the data which is present in our table, but still you have all the valuable information which you want because department table is still there. So you can know that if a person is in IT department, which is the manager and what is the salary of that particular person. Even if you delete the entire record which is present in the employee table, still you sustain the department information or the valuable information which is present there. So deletion anomaly is also taken care or reduced. Now coming to the third, that is updation anomaly. So consider that if you want to update the salary of the HR people, you just need to go to this department table and you just need to update it here. So there is a only single update which you need to do. Earlier you need to do it at multiple places because it was present in this particular table, but now since it is divided into 2 tables, you just need to update it at one place and it will start reflecting for each and every employee. Now coming to the types of normalization, so basically there are 3 types of normalization. The very first is first normal form or 1NF, then second normal form, and the third normal form. The BCNF or Boyce code normal form is an advanced version of the third normal form. So we would be learning about each and every normal form in detail. We will understand that how these normal forms are helping us to reduce the data redundancy. So in simple terms, you can say normalization help us to reduce the data redundancy or duplicacy which is present in our data. It doesn't guarantees to remove the entire duplicacy or redundancy of data, but it guarantees to reduce the redundancy which is present in our data. So what is this denormalization? This is the opposite of normalization. So whatever things we do in normalization, we just do the opposite in denormalization. It involves intentionally introducing some redundancy into a well-normalized database schema to improve query performance. Now in normalization, what we used to do is we used to reduce the data redundancy which is present in our table. Consider that there is a table of employee which is having employee ID, employee name, employee age, as well as this department details such as employee department name, department ID, department salary. Now in this particular table, we used to encounter some data redundancy or duplicacy because of rows as well as column. So row level duplicacy was make sure introducing the concept of primary key. We used to make an attribute such as ID as primary key, and now there couldn't be any null or duplicate values which is present in our ID column. So row level duplicacy was reduced. Now for column level duplicacy, we encountered that there were some columns which are having the same details like the department manager and salary whenever there is a IT department, and whenever there is a HR department, it used to remain same for the set of employees who are having the same department. Now for that, what we used to do is we used to normalize the table and we used to break the table into 2 subtables or more tables so that we can reduce the column level duplicacy which we were encountering. But in denormalization, what it says is we intentionally introduce some redundancy into a well-normalized database schema to improve the query performance. Now in normalization, we used to break the tables into subtables, 2 or more tables. So this was the earlier table which was present. Now there are subtables to reduce the data redundancy. Now this is an employee table, this is the department table, and this is the salary table. Consider I want the detail of an employee who is having ID as 2, and I want the details of its department as well as his salary. So I want all the employee details, I want all the department details, I want all the salary details for an employee who is having ID as 2. Now for that I have to make query into this particular table, and this table as well. And as the table increase, the queries also increase. Now we have to make different type of joins to get some data from the department as well as salary table. So because of that, our query is not very much optimized, or it takes a lot of time to fetch from each and every table, because there could be a possibility that the data is present at the very last of department table, the data is present at the very first of salary table, and because of that we encounter some issues like the query is taking a lot of time. Now the query, if it's being used in an API, the API is taking a lot of time, our SLAs increase. So because of that we can encounter some time issues, some speed issues, and much more things. So because of that we introduce the concept of denormalization, that we are intentionally introducing redundancy, but if all the data is present into the same table, the query time would be very less. So consider if you wish to find the salary of Rahul. So to find the salary of Rahul, first we need to find the department of Rahul. So first we have to make the query into the employee table to find the department, and once we get the department of Rahul, that is IT, then again we have to make a query in this department table to fetch the salary of Rahul. So you can see that we are making multiple queries. So multiple queries can increase the time, can reduce the speed, and our API can take a lot of time to provide us the result. So what are the benefits of denormalization? First one is faster queries. So it can reduce the need for complex joins between tables during queries, which can eventually improve the speed of retrieving the data, and it can give the data very fast. Now the second benefit is the queries would be simpler, because there are no joins which are being involved. There are no 3 or 4 tables in which we are making queries. So the queries would be very less complex. It can simplify the queries by allowing them to be executed on a single table instead of requiring joins across multiple tables. So in normalization, we used to break a single table into multiple tables. Now we need to make queries into these tables. So because of making queries into different tables, the time also increases and the queries also get complex. In denormalization, we used to combine all the tables into a single table, even if we know that the data redundancy can occur, but still we are combining it into a single table, and because we are combining it into a single table, the time always reduces and the queries are also simple, so there are not complex queries. Now with advantages, there are always disadvantages. So let's see the disadvantages. So first disadvantage is increase data redundancy. As I told that we introduced the concept of normalization to decrease the data redundancy. But since in denormalization we are again combining all the table into a single table, which is we are breaking the normalized table into a denormalized table, so we can say that the data redundancy has increased. Now the second is less data consistency, because if we are combining everything in a single table, consider that if I need to update the salary of a person who is working in IT department, and if somehow I miss to update for any of the employee, the salary would be different for both employees who are working in IT department. So that would be a data inconsistency. Now the third is denormalization can make the database schema less flexible for future changes like adding, modifying new data elements. So we learned about the insertion, updation and deletion anomalies. So that can occur because of denormalization. We can't go ahead and add any of the data of any of the new employee who has joined the company, because right now I don't know the department manager and salary details of that particular employee. Or consider that there is a new department, supply chain, which is introduced in our company. For now there are no employees who are present in supply chain, and since ID is a primary key, we can't make it as null and we need to insert a data, but right now we don't have any data. So these type of issues can happen whenever we denormalize the table, but the only advantage is it makes the queries faster and it simplifies the query. Now, as the term suggests, functional dependency. So whenever there is a kind of dependency which is present in form of any function, we can call it as functional dependency. You might have heard about the terms such as equations or functions in maths. Now, if there is a function given y equals to fx, that is y is a function of x, where fx is equal to x square plus 2x plus 1. So if I know the value of x, I can determine the value of y. So what I'll do, I'll just put the value of x here. So that would be 1 plus 2 plus 1, that is 4. So here, if I know the value of x, I can determine the value of y. So y is a function of x, so we can say that y is functionally dependent on x, because whenever we know the value of x, we can find the value of y. Now, in functional dependency, it describes the relationship between the attributes in a relation. So attributes you can say as columns, and relations you can say as table. So whenever there is a table, consider that this is the table name is R, or we can say it is a relation where we have two attributes x and y, we can say columns. So if y is functionally dependent on x, it means if I know the value of x, I can determine or find the value of y. So a functional dependency is a constraint between two set of attributes in a relation from a database. So it's not important that it will always happen between single attributes. There could be a set of attributes which could be functionally dependent on some set of attribute. So consider that in a table there is a primary key. Now primary key can either be a single attribute or can be a set of attribute. So if roll number is something which is being repeated for each or every person in a combined branch like CSE, EC, so there could be a possibility that in CSE also a person is roll number 1. In EC branch also there is a person with roll number 1. So what we will do is we will take a composite attribute, we will combine two attributes to make it as a primary key or a unique identification key, using which we can find the details of that particular person or that particular student in a college. Now for a relation table R, if there are two attributes x and y, then we can say the functional dependency is x determines y, or we can say y is functionally dependent on x, where y is called as dependent and x is called as determinant. So x is called as determinant because if we know the value of x, we can determine the value of y, and y is somehow dependent on the value of x. So if I know the value of x, I can find the value of y. Consider in a normal table that if there is a roll number and there is a name. So if I know the roll number of any person, I can tell the name of that particular person. So roll number is kind of a determinant and name is kind of a dependent, and name is functionally dependent on roll number, because if I know the value of roll number, I can determine the value of name. So attribute y is functionally dependent on attribute x. So y is functionally dependent on attribute x, or we can say x determine y. Now, if x is equal to 1, we can find the value of y. The same example which I show here, that if we know the value of x, we can find the value of y here as well. Now, functional dependency x determines y. X, y is a subset of the relation. So, if there is a table or there is a relation, then x and y is always a subset of that particular relation. Here I am talking about subset, but what subset exactly is? So let there be two sets A and B. Now A is having value 1, 2 and 3, and B is having value 1, 2, 3, 4 and 5. Now A is a subset of B because every element of A is also an element of B. So we can say that A is a subset of B because every element of A, 1 is also present here, 2 is also present here, 3 is also present here. So A is a subset of B because all the elements which is present in A is also present in B. But vice versa is not true because 4 and 5 is not present in A. So we can say that A is a subset of B because every element of A is an element in B. Now here there is a table employee ID, employee first name and employee last name. So here there are some of the functional dependency which is provided. So first is that employee ID will always determine employee first name. So let's see if employee ID can determine employee first name. So if I know the employee ID as 1, is there any employee ID with 1 existing in this particular relation? No. Now in correspondence to 1, what is the employee first name? That is Riti. So if I know the employee ID, I can know the employee first name. first name. So we can say that employee first name is functionally dependent on employee ID, or if I know the employee ID, I can find the employee first name. So you can also say that in functional dependency, the X is kind of a unique identification key. Unique identification key. So basically this is a unique identification key which help us to identify or determine or find the value of Y when we know the value of X. So for this employee ID also there is no 2 which is present in this particular column, so the value would be Rahul. For 3 there is no 3 which is present in this employee ID column, so we can say the value would be Suraj. So we can say that employee ID is determining employee first name, or employee first name is functionally dependent on employee ID. So employee first name is functionally dependent on employee ID. In the same way, employee last name is also functionally dependent on employee ID. Now here you will say that you have written the functional dependency, but how will we identify that if there is a table or there is a relation, what are the functional dependency which are existing? So the first way to determine that is that if there is X which is determining Y, X can always be a set of attributes and Y can also be a set of attributes. So we can also say that employee ID and employee first name both are determining employee last name. So X would be this set of attribute which is employee ID and employee first name. In the same way, we can also say that employee ID is determining employee first name and employee last name. So here Y is also a set of attribute. So this thing first we need to understand that X determining Y, X can always be a set of attribute and Y also can always be a set of attribute. Now how we will know the functional dependency in a given table? Now according to functional dependency definition, if there is a relation R, X determines Y, where X and Y are the attributes of the relation, and X can be an attribute or a set of attribute, Y can also be an attribute or a set of attribute, and Y is functionally dependent on X. Now here, can you say that X or the one which is a determinant is always a primary key? So can we say that X is a primary key? The answer is no. It's not always true that X will always be a primary key. This is a unique identification key, but it's not a primary key. It can be a primary key, but it's not important for X to be a primary key. It should always be a unique identification key. Now, how do we find that if there is a X which is present, or if there is an attribute which is present, is acting as a determinant or not? So as I told that it is not always true that it will always be a primary key. So there could be a possibility that there is some duplicacy in this employee ID column. So again, the employee ID is 1, the name is considered Ria, and the last name is Singh. So here you can see now employee ID is having 2 ones which is present in the table. So it is not unique. So primary key violation happens because this particular employee ID or this particular attribute doesn't have unique values. Now if we want to now see that if this employee ID determines employee first name is true or not for this particular table, what we need to do is if there are 2 tuples, or you can say 2 records, and the value of X is similar for both of the records, then the value of Y should always be similar, so that these are functionally dependent. So if there are 2 tuples T1 and T2, and if T1.x is equal to T2.x, that is this is equal to this, then T1.y should always be equal to T2.y for the functional dependency to exist. So let's see, is T1.x equal to T2.x? 1 is equal to 1. So this is true. So let's see if T1.y is equal to T2.y or not. So T1.y is Riti and T2.y is Ria. So is T1.y equal to T2.y? No. So now we can't say that employee ID determines employee first name, because consider that if I provide the employee ID 1, what would be the value of Y it will return? Because right now 1 is having the value as Riti and 1 is also having the value as Ria. So now employee ID is not determining employee first name. But what if here the value is written as Riti? So now, is the employee ID determining the employee first name? Yes, because 1 is always corresponding to only one value. 1 is not corresponding to 2 values. 1 is always corresponding to only one value. So this is the criteria which we use to follow to find the functional dependencies which are present in our relation. So if there are two tuples who are having the same value, such as like the same record is present in that particular two tuples, then we should always check the value which is being determined or which is functionally dependent on that value. So if there is employee ID which is having values such as 1 and 1, then we need to check that what is the corresponding value to this one, because there could be a possibility that this one is giving me Riti and this one is giving me Riya. So one is having multiple values. One should always hold single value because this is a unique identification. If I say that one is also giving me Riti, one is also giving me Riya, so the unique identification does not exist. X shouldn't be a primary key. It can or it cannot be, but X should always be a unique identification. So this is called as functional dependency. So whenever we encounter that if there is an employee ID column which is having unique values or where there is a primary key, we don't need to check for all those things, because if it's a primary key, it will always determine some unique values only. But if there are some duplicacy which is present in this employee ID, then we need to check this condition that for given two tuples, if the value of X is similar, the value of Y should always be similar. If it's not similar, then it's not functionally dependent or the functional dependency does not exist. I know this can be a bit confusing, but when we will learn about normal forms, that would be clear more and more. For now, you can just understand that in functional dependency, there is a relation and then there are some attributes. One attribute is functionally dependent on another attribute. It basically means that if I know the value of X, I can determine the value of Y. X and Y can be a set of attributes. X is not always needed to be a primary key. It can or it won't be, but X should always be a unique identification key. That is, for one value of X, there should always be one value of Y. There shouldn't be a multiple values of Y. Now there are some properties of functional dependency, or we can also call it as inference rules. Now what are those properties? So the very first property is reflexivity. Now what is this reflexivity? So if there are two attributes X and Y, where Y is functionally dependent on X and X determines Y, we can say that if Y is a subset of X, then X determines Y or X determines X. Now how this comes X determines X? So here I told that Y is a subset of X. So Y is always having some values which is present in X. So Y will always have the value X. So we can say that X determines X. So a particular attribute can always determine itself and it can determine Y if Y is a subset of X. So X determines X always holds true in terms of the reflexivity property. Because Y is a subset of X, so Y would always be having values which are having X. So X determines X always holds true. Now the second property is augmentation. What does this mean? That if X determines Y and if we are augmenting Z here, then XZ should always determine YZ for any Z. So consider that there is an employee ID which determines employee name. Now if I augment or add something, so if employee ID, I add an employee phone number. So employee ID, employee phone number both together can determine employee name and employee phone number. So I can see that if something is added at LHS and the same thing is added at RHS, then there would be a functional dependency which will exist between this combination. Now the third one is transitivity. So what this transitivity says us, कि if X determines Y, so if X is an attribute which determines Y and then Y is an attribute which determines Z, then X is an attribute which will always determine Z. So if X determines Y and Y determines Z, then X will always determine Z. We don't need to check for this dependency if this exists or not. If X is an attribute which determines Y and Y is an attribute which determines Z, then we can say that X will determine Z as Y is common between them. So this is called as transitivity. Now the fourth one is union. Now what union says is if X determines Y and X determines Z, since LHS is common in both the cases, we can say that X will determine YZ. So since X determines Y, X also determines Z. So since employee ID determines the employee first name and employee ID determines the employee last name, then we can say that employee ID can determine employee first name as well as employee last name. So there is a union which happens whenever the LHS is equal. But the vice versa is not true. If I say YZ determines X, I can't say that Y will determine X and Z will determine X. This is wrong. Because again, YZ is something which is a combination which is helping me for the unique identification, or this is a unique identifier or a key. So if the both of these key are helping me to determine one attribute, I can't say that a single attribute can determine this particular attribute, because the composite version of this is helping me to determine the attribute. So if X determines Y and X determines Z, we can say that X determines YZ, but we can't say that if YZ determines X, Y will determine X and Z will also determine X. That is wrong and that is not true. Now the fifth rule is rule of decomposition. So if X determines YZ, we can say that X determines Y and X determines Z, which is the same which we learnt in union. So it's just the reverse of union. So if X determines YZ, we can say X determines Y and X determines Z. So the determinant can never be broken. Determinant can never be broken. If it's a set of attributes, it can't be broken into single attributes and determine something, because the set of attribute is helping in the unique identification, not the single attributes, right? So this can't be broken. The RHS can be broken. The dependent can be broken, but the determinant can't be broken. Now, what are the types of functional dependency? So there are two types of functional dependency. One is trivial and the second one is non-trivial. There are more, but basically now we need to know about these two only, trivial and non-trivial. So let's see what is trivial. So functional dependency X determines Y is trivial if Y is a subset of X. So it says that if Y is a subset of X, X can determine Y and X can also determine itself, that is X. So this particular dependency is always valid. We don't need to go ahead and check in our table, because X can always determine X. Employee ID can always determine employee ID. If I say that employee ID is 1, find the employee ID in the table, I can always find the employee ID because I know the employee ID is 1 here. So X will always determine X. This is a valid dependency. This doesn't need to check that if there are some employee IDs which are present, if again there are some employee IDs which are present, because we are seeing in the same column, or you can say in the same attribute itself. Also, since Y is a subset of X, Y will be having values or the elements which is present in X. So we can say X will determine X. So we can also say it as X determines X. Now consider that here there is a dependency given where employee ID and employee first name is determining employee ID. Now this is Y and this is X. Now in Y we have employee ID and in X also we have employee ID. So we can say that Y is a subset of X because the element which is present in Y is also present in X. So we can also say that employee ID determines employee ID. And employee ID, employee first name determines employee ID. Now, this is trivial because employee ID is a subset of employee ID and employee first name. So, we can say that trivial dependency exists whenever X intersection Y is always Y. So, whenever we are doing an intersection between them. So, we are doing an intersection between employee ID and employee first name. So in intersection, we used to provide the common which is present between them. So in employee ID and employee first name, employee ID is the common one. So we give the value as employee ID for a result. So X intersection Y always gives us Y. Y is employee ID. So here we get the employee ID. So this is the trivial dependency. Now what is non-trivial dependency? A functional dependency X determine Y is non-trivial if Y is not a subset of X. So Y is not a subset of X, basically, which means that if there are some values which is present in Y, or if there are some attributes which is present in Y, it's not necessary for that attributes to be present in X. So here if you can see, X is having employee name and Y is having employee ID. So employee ID is not present in employee name, so Y is not a subset of X. So these dependency needs to be proved, because so right now I am saying that employee ID is getting determined by employee name, or employee ID is dependent on employee name. But is this true? Like we have to check that if this is valid or not. In trivial, what used to happen is x determines y and y is always a subset of x. So y always contains some element which is there in x, or y is always having some attributes which is in x. So this is always true. But when x determines y and y is not a subset of x, then we need to prove that point ki, okay, if employee name is determining employee ID, I can check from my table if this functional dependency is present or not present. So functional dependency x determines y is not trivial when the y is not a subset of x. So if there is x as employee ID and y as employee first name, we can say it is non-trivial because employee first name is not a subset of employee ID. So employee first name does not have any element which is there in employee ID. So here if we do x intersection y, we get 5 because x intersection y does not gives us anything because there is nothing common between employee first name and employee ID. So it will give me 5 or it will give me empty. Now what is this attribute closure or closure set? As the name suggests that it will give me a set of attribute. But what is it exactly? So let's see. Attribute closure help us for identifying candidate keys, checking for functional dependencies, and then normalization. So whenever we need any kind of help in finding the candidate keys which is present in our relation or the super keys, and whenever we need any help in checking the functional dependencies present in our table, we use the attribute closure. So whenever there is an attribute x, it can be an attribute or you can also call it as a set of attribute. So whenever there is an attribute or a set of attribute, the closure set of this particular attribute is denoted by the plus sign and it gives me the set of all the attributes which can be determined by this particular attribute x. So closure of any attribute is denoted by plus sign and it gives me all the attributes which are present in the relation which can be determined by x. So here x is an attribute or set of attribute which gives me all the attributes in a relation which can be determined by x. So consider that there is a relation in which there is a functional dependencies x determine A and there is one more functional dependency x determine B. So since x is determining A and x is determining B, if I find the closure of x according to the definition, it should give me all the attributes which can be determined by x. So that would be A and B. So A and B would be the closure set of x. So x closure gives me all the attributes which is present in the relation which can be determined by x. So let's see a practice question on how we can determine the attribute closure or closure set on some of the attributes which is present in a relation. So consider we have a relation R with attributes such as A, B, C, D and E. And there are some functional dependencies which are given as such. A determines B, B determines C, C determines D and D determines E. Now this A determines B says that if we know the value of A, we can find the value of B or B is functionally dependent on A. So these all things are being taught in the functional dependency video. So if you're not understanding this, you can go ahead and watch that video first and then come to this video. Now, how we can find the closure set of some of the attributes which is present in this table. So let's see. So the very first step is now according to the rule of reflexivity, all the attributes can determine their self. So according to the rule of reflexivity, it says if y is a subset of x, then x can determine y. So since y is a subset of x, y would always have all the elements which is present in x. So we can also say that x can determine x. We can replace y with x because y would be having all the elements which is present in x. So we'll just use the rule of reflexivity and derive some of the functional dependencies, that is A will determine A, B will determine B, C will determine C, D will determine D and E will determine E. So all the attributes can determine themselves according to the rule of reflexivity. Now the second step is, now according to the rule of transitivity, if A determines B and B determines C, then we can say that A can also determine C as B is common between them. So whenever A determines B and then B is an attribute which determines any other attributes, then A can also determine C. So since in the question we have some of the functional dependencies present, so let's use this functional dependency and let's use the rule of transitivity to derive some more functional dependency which will be helpful for us to find the closure. So let's see for A. So here it is given A determines B and then B determines C. So since B is common between them, can we say with the rule of transitivity that A will determine C? Yes, we can say. So the first functional dependency which we derive is A determines C. Now B is determining C and C is determining D. Now C is again common between them. So we can say B will determine D. So B will determine D is the second dependency. Now C determines D and D determines E. Again D is common between them. So we can say that C will determine E. So C will determine E is the third dependency which we got. Now since we have got 3 new functional dependency and these are also existing. So let's see if there are more dependencies which can come. So since here we can see that A determines C and here is there any C present? Yeah, C determines D. So we can say A determines C and C determines D. Since C is common between them, then A will determine D. So A determines D is another dependency. Now since A determines D, let's see that if there is any functional dependency with D. Yes. So D determines E. So we can say that A determines D, D determines E. So A will determine E. So A determine E is also a functional dependency. Now here E is present. So is E determining any of the dependency? No. So these will be all the dependencies of A. Now coming to B. So B determine D. Is there any D determining any of the attribute? Yes. So D determines E. So we can say since D is common between them, B determines E. Now coming to E. Is there any E which is determining anything? No. So these will be the dependencies of B. Now coming to C. So C determines E and since E doesn't determine any of the attributes, so this will be the only functional dependency for C. Now coming to the third step. Now according to the rule of union, if the determinant is same, we can combine the dependent. So according to the rule of union, if X determines A and X determines B, we can combine the dependent since the determinant is same. So we can say X will determine AB. So since we have all the functional dependencies with us using the rule of reflexivity and transitivity, let's see that how we can find the union. So for A, since A determine B, A determine C, A determine D and A determine E using transitivity rule and A determine A using reflexivity rule. So A will determine all A, B, C, D, E. In the same way we find for B, C, D and E. So B will determine C, D, E, B. C will determine D, E, C. D will determine ED and E will determine only E. So here the position doesn't matter. We can also write it as B, A, C, E, D. Like in any manner we can write. It's just that all the dependents should be present. So this step 4 is we have to find the closure set of attribute. So what it says is whenever we are finding closure of any of the attribute or the set of attribute, it contains all the attributes or all the set of attributes which can be determined by the attribute for which we are finding the closure. So here A closure will contain all the attributes which can be determined by A. So since here we have find all the functional dependencies and here we have find all the attributes which can be determined by A. So here you can say A can determine A, B, C, D and E. So A closure will have A, B, C, D and E as mentioned here. So A closure will be having A, B, C, D, E. In the same way B closure will be having this, C closure, D closure, E closure. So here you can see that we are finding the closure of set of attribute. So whenever we need to find the closure of set of attribute, what we do is firstly we write all the attributes which can be determined by A. So that is A, B, C, D and E. And then we write all the attributes which can be determined by B. That is B, C, D, E. But that is already present in the set, so we don't need to duplicate or repeat it. So this is the attribute closure of AB plus. It will be having all the attributes which is present in the relation. So it will give me all the attributes which can be determined by A, then all the attributes which can be determined by B. So combined it gives me A, B, C, D, E and E. Now since we learnt about attribute closure in the last video, we would be using that attribute closure and finding super keys in our given relation or in our given table. Now let's find the candidate key, super key, prime and non-prime attributes. So what is super key? Super key is a set of attributes whose closure contains all the attributes given in a relation. So basically super key is attribute or you can say a set of attribute. So X is a super key. It can be a single attribute or it can be a set of attribute whose closure contains all the attributes which are given in a relation. So consider that there is a relation or there is a table. In that particular table, attributes basically means the columns. So consider that there are 3 columns A, B and C. And if the closure of X contains all A, B and C, then this is qualified to be a super key. So whenever a closure of any of the attribute or set of attribute contains all the attributes which is present in a relation, we can call that attribute or set of attribute a super key. Now, a key combination of all possible attributes which can uniquely identify two tuples. So super key is also a key which can uniquely identify two tuples. A key can be a combination of attributes or can be an attribute. Now how to find the super key? So there are certain steps which we need to follow to find the super key. So let's see. So the very first step is we have to identify all the attributes. So the first step is identify all the attributes which is present in our table. So consider that right now it's A, B and C. So we have identified all the attributes. Now the second is we have to analyze the functional dependencies and find the closure. So how we used to find the closure is, consider that if we are finding a closure of A, so we have to see that what all attributes does A determines. So consider that A determines B, A determines C, A determines D. So closure of A would contain B, C, D, and from the reflexivity property, A can also determine itself. Because according to the rule of reflexivity, an attribute can determine Y whenever Y is a subset of X. So what does this mean? Y is a subset of X. Basically, Y will have all the elements which is present in X. So can we replace this Y with X here? Yes, we can do. So we can say that an attribute can determine itself using the reflexivity property. So A can determine A. So we can say the closure of A contains all the attributes which is present in our table. So this can possibly be a super key. So we have to analyze the functional dependencies like A determines B, B determines C, C determines D, any of the functional dependency, and then we have to find the closure. Now we have to generate the power set. So right now I am saying that A is my super key, but super key can be an attribute or can be a set of attribute. So AB can also possibly be a super key, AC can also be a super key, consider BC can also be a super key. So we need to find out that what all attributes or set of attributes can be the super key. So for that we generate the power set. In that power set we get all the attributes or all the possible combinations which can be of super key, and then we determine that if that possible combinations closure is giving me all the attributes which is present in the relation or not. So if it's not giving, it's not a super key. If it's giving, then it's a super key. So if A has n attributes, the power set of n will be having 2 to the power n subsets. So consider that here X is having 3 attributes. So what would be the power set of X? So that would be 2 to the power 3, that is 8. So power set of X would be having total 8 sets. So total 8 combinations, and in that combinations we can check that which particular combination or which particular single attribute qualifies to be a super key. Then the final check is check for super key property. So we have to check for the super key property. So from here we have generated all the subset. Consider a subset A, B, C, we can say AB, AC, BC. We have generated all the power subsets. Now for these power subsets, we have to take the closure of all these power subsets, and we have to see that if the closure determines all the attribute, or if in the closure all the attributes are present which is there in a relation. If it is there, then that particular set can be a super key. If it's not present, then we will discard this from the final result. So for each subset in the power set, check if it can uniquely identify each tuple in the relation. So let's solve a practice question where we will be finding all the super keys. So here the relation is given as R, A, B, C, and the functional dependencies are given as A determines B and B determines C. So these are the functional dependencies which are provided, and this is the relation which is provided along with all the attributes. So what was our step 1? We have to identify all the attributes. So to identify all the attributes, we can see that there are 3 attributes in a relation. So we will just note it down, A, B and C. So in step 2, we have to analyze the functional dependencies and find the closure. So here you can see that we have been provided with 2 functional dependencies, A determine B and B determine C. So this is provided. Let's derive some of the functional dependency. So since A determines B and B determines C, can we say since B is common between them, A will determine C from the property of transitivity. So we can say that A will determine C is a property which we have derived, or is a functional dependency which we have derived. Now we have derived A determines C. Now each attribute can determine themselves. So we can also say A will determine A, B will determine B and C will determine C. Apart from that, we can't find any other functional dependency. So these are the functional dependency which we have calculated, and these were the provided ones. Now, from this functional dependency, if we find the closure of A, we have to write down all the attributes which A determines. So A can determine C, so we will write C. A can determine A, so we will write A. And A can also determine B, so we will write B. So the closure of A will contain C, A, B. So here you can see that A closure has C, A, B, which is also the attributes which is present in our relation. So can we say that A is a super key? Yes, we can say that A is a super key because A closure determines all the attributes which is present in our table, that is A, B and C. Now B closure, so B closure will contain B and C and it does not determine A, so there won't be any A, and C closure would be only having C. So B closure and C closure does not qualifies to be a super key. This particular thing you can also do after the generation of power set, or you can do before the generation of power set. I'll tell you that why before the generation of power set this is useful. So the closure of A gives or determines all the attributes in the table, so we can say it's a super key. Now, the third step is how do we find all the super keys? So for that, we have to find the power subset. So we have to find the power set of A, B and C. So since I told that the power set of any of the given set is 2 to the power, consider that this set is x, so it's 2 to the power x. So here it will be 2 to the power 3, so here it will be 8. So the power set of this particular set would be having 8 elements. Now let's understand about power set. So power set is the set of all subsets of a given set, including the empty set as well as the set itself. So consider that there is a set x. X is having elements such as A and B. Now in this, if we calculate the power set of x, it will be having set of all subsets. So basically it will be having set of all subsets of A and B, including the empty set as well as the set itself. So set itself is AB, empty set is this which is having no element, and the subset will be A and B. So the power set of x equals to AB would be having these 4 elements. Now the power set of x is denoted by 2 to the power x. So we can say that the power set of x would be 2 to the power x, which is 2 to the power number of elements, that is 2 to the power 2, which is 4. Now let's see if there are 4. So 1, 2, 3 and 4. So the power set of x is having 4 sets. Now let's take a simple example, the same example which I explained above. So the power set of x would include the following subsets. One is the empty set, this one. One is the single element set, that is A and B. And one is the full set itself, that is AB. So the power set Px would be Px is equal to 5, which is an empty set. Then A, B and AB. In this way, we can calculate the power set of any given set. So the power set of ABC would be having firstly 5, or you can say empty set. Then we will be having single elements, so A, B and C. Then we can have the combination, so we can say AB, AC, then BC, and then we can say the entire set itself, so that would be A, B and C. So here you can calculate that there are 3 elements, so it will be having 2 to the power 3, that is 8 sets. So if we calculate here, so 1, 2, 3, 4, 5, 6, 7, 8. So we have got 8 sets overall. Now to calculate all the super keys, what we will do is we will take the closure of all those 8 sets. So let's take a closure. So first is this empty set. So the closure of empty set wouldn't give anything, so it's not a super key. Second, A, we calculated that A is a super key after taking the A closure. So we can say that it is a super key as its closure determines all the attributes in a relation. Now the second is B. For B also we calculated that B doesn't determine A. So B does not have all the attributes which is getting determined in the relation. So B is not a super key. Again C only have C in the closure. So C is not also a super key. Now the next is AB. So for AB, do you need to determine the closure and then conclude that it is a super key or not? If you remember, in the first step, we calculate the closure of the single attributes, that was A, B and C. And from that we found out that A is a super key, B and C were not a super keys. So since A is a super key, can we say that if any attribute is augmented with A, that will also be a super key? Because if I take a closure of AB, A closure will only contain all the attribute which is present in the relation. So if we augment anything with A, that will also be a super key, right? Let's take a closure of AB. So if we take a closure of AB, we can say that A determines A, B and C, and B will determine B and C, which is already present here. So we can say that if anything is augmented with a super key, that also becomes a super key. So we can say that AB is a super key since A is already a super key. So adding B still keeps it a super key. So we can say AB is a super key. Now coming to AC, the same thing, that A is always a super key. So if we augment anything with A, that will also become a super key. So AC is also a super key since A is already a super key. So adding C still keeps it as a super key. Now coming to BC, neither B, neither C, both of them are not a super keys. So we have to take the closure and we have to find out that if the closure of them gives us a super key or not. So if we take the closure, B gives us B, C gives us C. B does not determine A, either C does not determine even B or C. So BC closure does not give me all the attribute which is present in our table. So we can say that BC is not a super key as B determines C but does not determine A. Now coming to A, B and C. Again, since A is already present here, if we augment anything with A, that will be a super key. So we can say it is a super key as A is already a super key. So adding B and C keeps it as a super key. So we can say that there are 4 super keys for the given relation, that is AB, AC, ABC and A. Now consider that right now we were dealing with only 3 attributes. So calculating the power set was easy, but consider that someone asks you to find the super keys for a given relation where there are n number of attributes. Would you go ahead and find the power set and then find the closure? It would be a very tedious task. So for that we have a formula. So to find the maximum number of super keys, we can use the formula which is 2 to the power n minus k, where k is the candidate key with k attributes. That is, considered that k is a key which is having a k number of attributes and it is a candidate key, and n is the total number of attributes in the given relation. So using this formula, we can find out the number of super keys, but we should be knowing that what is the candidate key. So in the next video, we would be learning on how we can find the candidate keys in a given table. After that, you can use this formula to find the super key. When there is one candidate key, we can say that it is 2 to the power n minus 1 since k is the candidate key and there is only one key present here. So we can say it is 2 to the power n minus 1. When there are 2 candidate keys, so for the first candidate key, it will be 2 to the power n minus 1. For the second candidate key, it will be 2 to the power n minus 1. And then in these both candidate key, there could be occurrence of both the candidate keys together. So for that, we will be subtracting 2 to the power n minus 2. That is the combination of both the candidate keys. Now, what is a candidate key? So a candidate key is basically a super key whose proper subset is not a super key. So let's understand term by term. What is a super key? So an attribute or a set of attribute is considered to be a super key if its closure gives all the attributes which is present in our relation. So consider that there is a relation or there is a table in which the attributes are A, B and C, and if the closure of a attribute or a set of attribute gives us all the attributes which is present in our relation, these are considered to be a super key. Now what is this proper subset? So consider that if we are having a set which is having elements such as A and B. Now if we want to take the subset of this, so it will be having phi A, B and AB. In proper subset, what it says is it should have all the elements except the element for which the subset we are taking. So it should be having all the elements. It should be having phi or empty set. It should be having A. It should be having B, but it shouldn't be having S, that is AB. So if we are taking a proper subset of a given set A and B, it should be having individual A and B, but not AB, because that is already present in S. So here we can say that proper subset of S is all the elements which is present in S except the elements which is present in the set S itself. So all the elements of A are also the elements of B. So all the elements of, consider that this is a set A. So all the elements of set A are also the elements of set B, and set B has at least one element that is not in A. So in A, if we take the subset of this, so it would be A, B, AB and phi. So at least AB, there is one set which is not there in B. So we can say that B is a proper subset of set A because B has at least one element that is there in set A but not in set B. So it has all the elements which are there in set A, but there is only one element which is there in set A but not in set B. So this is called as proper set. So we can say that whenever we are calculating the proper subset of a given set, it has all the elements which is present in the set except one element which is the set itself. So now coming back to the definition of candidate key. So it says a super key whose proper subset. So consider that AB is a super key right now, and the proper subset of AB is A, B and phi is not a super key. So how we can find the super key? We have to take the closure. So we will take the closure of all three, and if the closure of all three are not super keys, we can say that this is a candidate key. If any one of them tends to be a super key, we can't say that this is a candidate key. So first we have to find out the super key, then we have to take the proper subset of super key, then we have to find that if the proper subset is a super key or not. So for that we will take the closure, and when we take the closure we will know that if it is determining all the attributes of a given table, and if it's not determining, we can say that this particular is not a super key, and if it's determining, we can say that this is a super key. And if any one of the proper subset is a super key, we can say that AB is not a candidate key. I know it might sound confusing, but let's see from a practice problem, and then you will get a clarity on how we can find out the super key and the candidate key in a given relation. Now, there are two things you need to know before proceeding ahead with finding the candidate key. First is prime attribute and second is non-prime attribute. Let's see what are these. So an attribute that is a part of candidate key, we call it as prime attribute. So consider for now AB is our candidate key, and in our relation there are three attributes A, B and C. So we can say that A and B are the prime attributes as they are part of candidate key. And non-prime attribute are an attribute that is not a part of candidate key. So since there were three attributes and two of the attributes were part of candidate key, so we can say that C is a non-prime attribute and A and B are the prime attributes, since A and B are there in candidate key and C is not there in candidate. So how we can find the number of candidate key? Here are some steps we should follow to find the candidate keys. So the very first step is we have to take the closure of the entire attribute set. So consider that in our relation there are three attributes A, B and C. So what we will do is first we will take the closure of the entire attribute set. Now secondly, we will discard the dependents if their determinants are present. So what are dependents and determinants? Consider that there is a functional dependency A determines B. So we can say since A is determining B, this is determinant. And since B is functionally dependent on A, we can say that this is dependent. So in step B, what we have to do is we have to discard the dependents if their determinants are present. So since B's determinant is A and A is already present here, so what we will do is we will discard B from here. So we will discard the dependents if their determinants are present. Now after discarding, the final combination you get is a candidate key if its subset does not have a super key. So what we'll do is first we'll take the entire closure of all the attributes, and there we can find out that the closure will contain all the attribute of a given table because we are taking all the attributes closure, so it will be having all the attributes. So this is a super key. Now we have find out that there is a super key. From that super key, what we will do is we will go to the functional dependencies which are provided, and there we will see that if any dependent having a determinant is present here or not. If the determinant of any of the dependent is present, then we will discard the dependent. So here we have discarded B. Now we have left with AC. So can we say that AC is a candidate key? Right now, no, because we have to check if the proper subset of AC, that is A and C, is a super key or not. So what we will do here is we will take the closure of A, we will take the closure of C, and we will see that if it is a super key or not. If it's a super key, then we can say that this is not a candidate key if any of one of them is a super key. And if both of them are not a super key, we can say that AC is a candidate key. So right now we are assuming that AC is a candidate key. So we will mention A and C in the prime attribute. as the last step mention them in the prime attribute. Now in step 4, we will check that all the functional dependencies, and we will see in the right hand side if there is an attribute which has a determinant present in the prime attribute. If yes, mention that as well in the prime attribute and replace the dependent attribute with the determinant and check its candidate key. So right now we have found out that prime attributes are A and C. So we have to see that if A or C are lying in the right hand side of the functional dependency. So right now we have only one functional dependency where A determines B, and none of the prime attributes lies in the right hand side. But consider that if you have a dependency such as B determines C. So here you can see that C is a prime attribute and C lies in the right hand side. So what we can do is, right now we have calculated that AC is a candidate key. We can replace the dependent with its determinant. So right now AC is our candidate key. What we will do is, since C is the dependent and B is the determinant of C, we can replace C with B and we can check that if AB is a candidate key or not. So in this way we can find out all the combinations for which we can check that if they are candidate keys or not. If no prime attribute is available in the right hand side of functional dependency, we can say that there are no more candidate key, and the one key we made after discarding the dependent and checking for the super key is the only candidate key. So in this case, A and C, and the functional dependency was A determines B. Since there were no dependents which were present in the right hand side which were in the prime attributes, we can say that only AC is the candidate key. But when we added some additional functional dependency where B determines C and C is a dependent, so we can replace the dependent with its determinant, where AC can be replaced by AD, where C is replaced by B, and we can find out that if AB is a candidate key or not. So let's solve a practice question where we will find the candidate as well as super key for a given relation R, A, B, C, D, and the functional dependencies are given as follows. So let me just write it here. So there is a relation R, A, B, C, and D, and the functional dependencies provided are A determines B, B determines C, C determines D, and B determines A. So let's see that how we can find the candidate as well as super key. So let's find the super key. So to find the super key, firstly we will identify all the attributes. So all the attributes present are A, B, C, and D. Now in the second step, we will analyze the functional dependencies. So we will analyze that A determines B, B determines C. From this we can say A will determine C. Now B determines C, C determines D. Since C is common, we can say B determines D. Now B also determines A, and A determines B, B determines A. So A determines A is also a functional dependency. This is also the rule of reflexivity. We can say B determines B, C determines C, and D determines D. These are all the functional dependency. Now what we will do is we will find the closure for the single attribute. So firstly we will find the closure for A, B, C, and D, and we will see that if they are super keys or not. So let's find. So firstly we will find the closure for A. So A closure will be having A, since A determines A. So we can say A closure will be having A for sure. Then A closure will be having B, since A is determining B. Now A is determining B, B is determining C. So A is also determining C. So we can say C is also there. Now A is determining B, B is determining C, C is determining D. So we can say B is determining D and A is determining B. So A is also determining D. So we can say D is also there. Now let's calculate for B. So B closure would be having B. Now B determines C. So let's write C. And C determines D. So we can say B will determine D. So we'll write D. And B also determines A. So we can write A. So the B closure will be having B, C, D, A. Now let's take the C closure. So C determines D. C will determine itself and C will determine D. And then none of them. So C closure will be having C and D. Let's find the D closure. So D is determining nothing. So we can say D will determine only itself. So from here we can see that A closure and B closure are having all the attributes which are present in our relation or table. So we can say that A is also a super key and B is also a super key. Since C and D closure does not have all the attributes, so we are discarding them. So from here we got to know that A and B are super keys. Now we have to find the power set of this. So let's find the power set. So power set of A, B, C, D will be having 2 to the power 4 that is 16 sets. Now among that 16 sets, if there is any A which is in any set, that will be a super key. If there is B in any set, that will be a super key. So right now we will not go ahead and find the power set and then calculate the closure of that particular power set, and then we will find out the number of super keys. In the last video, I told you about a formula where we find the number of super keys using 2 to the power n minus k, where n is the number of attributes and k is the attributes which is present in the candidate key. So if we find the candidate key, we can find the super key. And right now we know that A and B are at least a super key. Right now we don't know that if A, B, B, C, C, D are a super keys or not, but for now we know that A and B are the super keys. So let's find the candidate key. So for finding the candidate key, first we have to take the closure of the entire set. So we'll take the closure of the entire set, that is A, B, C, D. So A, B, C, D closure would be having A, B, C, D, because each attribute will determine itself using the rule of reflexivity. So we can say that this is a super key. So now in the step 2, we have to discard the dependents if their determinants are present. So we have got this key as A, B, C, D. Now in this, we have to discard the dependents if their determinants are present. So the functional dependencies which are provided to us are A determines B, B determines C, C determines D, and B determines A. Now these are the functional dependencies which are provided to us. And also we can also say, using the rule of transitivity, A determines C and B determines D, since B is common between these two and C is common between these two. Now here we have to discard the dependents if their determinants are present. So let's start. So here B is the dependent and A is the determinant. Both are present, so we can discard the dependent, that is B. So now we are left with A, C and D. Now coming here, C is the dependent and B is the determinant. C is present but B is not present, so we will not take this into consideration. Coming here, D is the dependent and C is the determinant. C and D both are present, so we can discard the dependent, that is D. So we are left with AC. Now coming to this functional dependency, A is the dependent and B is the determinant, but since A is only present here, we will not look into this functional dependency. Now coming to this, C is the dependent and A is the determinant. A and C both are present here, so we can discard the dependent, that is C. Now coming to this functional dependency, B determines D. D is the dependent and B is the determinant. Any of the B and D is not present here, so we can ignore this. So after step 2, we are only left with A. Now, after discarding, the final combination you get is a candidate key if its subset does not have a super key. So we have to take the subset of A. So subset of A would be phi. Now phi closure does not gives me anything, so this is not a super key. So we can say that A is a candidate key because the proper subset of A does not gives me a super key. So we can say A is the candidate key. Now what we have to do is we have to mention them in prime attribute. So we will make a prime attribute and here I can mention A. So in the fourth step, what we will do is we'll check for all functional dependency and see if in the right hand side there is an attribute which has a determinant present in the prime attribute. So what we have to do is in the right hand side we have to see that if A is present or not. If A is present, then mention at this in the prime attribute. So we have to mention that particular determinant in the prime attribute, and then we have to replace this dependent with that particular determinant and check if it's a candidate key or not. So what we have to do is we have to check in the right hand side if A is present or not. If A is present in right hand side of any of the functional dependency, we have to replace A with the determinant and we have to mention that in the prime attribute. So for now we can see that there is only one place where A is in the right hand side and there is a determinant of A, that is B. So what we will do is we will mention that in the prime attribute and then we will replace A with B and follow the same step and see that if it's a candidate key or not. So let's see. So let's take a proper subset of B. So the proper subset of B is phi, and if I take the closure of phi, this is not giving me a super key. So we can say that B is also a candidate key. So here B and A both are candidate key. Now for B, we have to see that if B is present at the right hand side of any of the functional dependency, yes, B is present in this functional dependency, but A already is a candidate key, we have already seen. So we have to do nothing because now B is not present in any of the functional dependency in the right hand side. So if no prime attribute is available in the right hand side of functional dependency, we can say that there are no more candidate key, and the one key we made after discarding the dependent and checking for the super key is the only candidate key. So right now we can say that A and B are the only candidate keys in this particular relation. So this is how we find the candidate key. So here we can see that there are two candidate keys. Now for super key, we have a formula 2 to the power n minus k, where n is the number of attributes and k is the number of attributes in the candidate key. So let's see that how we can find the number of super keys when we know the candidate key. So here the candidate key is A and B. Now if I calculate for A, I can say that it will be 2 to the power n minus k. So n is 4 and the number of attribute in candidate key is 1. So we can say it's 1. So it would be 2 to the power 3. Now coming for B, it will again be 2 to the power n minus k. So n is 4, number of attributes, that is A, B, C, D, and then k is 1 because we are only calculating for B. So it will be 2 to the power 4 minus 1, that is 2 to the power 3. So for A we are having 2 to the power 3. For B we are having 2 to the power 3. But consider that we are calculating for the combination where A, B both are there and both are the candidate keys. So what we will do is, when we are calculating for both of the combination, there is A, B, C, D, and here if I say that A and B both are candidate key, so only C, D can have a combination with A, B, because if A, B is present anywhere, that would be a super key, right? So we have to calculate only for C, D. So we can say that here, since two attributes are candidate key, so in 2 to the power n minus k, n will be 4, but the number of attributes which is present in candidate key is 2. So we can say it would be 2 to the power 4 minus 2, it would be 2 to the power 2. So we have to just subtract that. So it will be 2 to the power 2 minus. So it will be 8 plus 8 minus 4, that is 12. So we can say that this is having 12 super keys and 2 candidate keys. So in this way we find the super key as well as candidate key in a given relation. Now before starting with first normal form, let's just re-revise about normalization. So consider that there is a table. Now table would be having some rows as well as columns. There could be a possibility that some of the rows have duplicate values, but there could be a possibility that some of the columns also have duplicate values. So from this we can conclude that there are two levels of duplicacy. First is a row level duplicacy and second is a column level duplicacy in a given table. Now row level duplicacy can be eliminated using primary key. Primary key makes sure that there is a unique identifier which uniquely identify each row in a given table. So we can eliminate the row level duplicacy using primary key. Now coming to the column level duplicacy. So column level duplicacy is not eliminated using primary key. So what we do is we divide the table into two or more tables so that the column level duplicacy is reduced, and this is what normalization is. So normalization is basically division of a given table into two or more subtables so that we can reduce the data duplicacy, or you can say data redundancy, and also maintain the data consistency along all the tables. Now coming to the first normal form. So first normal form is the first step in the normalization process which help us to reduce the data redundancy. As I told that normalization is oftenly used to reduce the data redundancy, or you can say data duplicacy, and first normal form is the first step in the normalization process which help us to achieve that. Now what it says is every table should have atomic values, that is there shouldn't be any multi-valued attributes which is present in a table. Now what is this multi-valued attribute? So consider that there is an attribute or a column phone number. Now one given person can have multiple phone numbers, like I can also have 2 phone numbers or 3 phone numbers. So we can say that phone number can have multiple values. So we can say a given attribute, whenever it holds multiple values, that is a multi-valued attribute. So to ensure that a given table is in first normal form, these are some set of rules a given table should follow. So the first rule is atomicity, which says that attribute should always have single value. That is, there shouldn't be any multi-valued attribute which is present in our table. If in our table there is a multi-valued attribute, we can say that our table is not in first normal form. Now coming to the second set of rule, that is uniqueness of rows. So we should always make sure that each row should be uniquely identifiable. That is, there should be a primary key which should exist in a table so that there is a unique identification key in our table. Now let's see about each and every set of rule, and let's see that if in a given table, if it's not in first normal form, how we can make the given table in first normal form. So the first rule was atomicity. It says that each column should contain only indivisible atomic values, meaning each attribute should hold only a single value. There shouldn't be any attribute which should be holding multiple values. So here we can see that there is a table in which we are having columns as ID, person name and order, and here we can say that ID is having single values, person name is also having single values, but when we see the order column, we can say that there are multiple values which is present in the order column for a given person. So we can say that order is a multi-valued attribute because order is having multiple values. So we can say that this particular table is not in first normal form since it is having a multi-valued attribute. Now let's see that how we can achieve atomicity or how we can make sure that our table is in first normal form. So there are three ways in which we can make a table in first normal form. So the first approach is, what we can do is, if there is a multi-valued attribute, we can repeat the other attributes twice or thrice depending on the values which is present in the multi-valued attribute, so that attribute can hold only single value. So here what we can do is, we can repeat the values in the ID and person name column twice, since we can see that there are two values for order for some of the entries. So we can repeat it twice to store single value of the multi-valued attribute order. So what we will do here is, we will write down all the columns or all the attributes which is present in our table, and then we will see that which is the multi-valued attribute. We will leave that particular attribute, and apart from that attribute, all the attributes which are present, we will repeat according to the values which is present in our multi-valued attribute. So here you can see that for Raj there are two orders, so we will repeat one Raj twice so that we can have single value for this particular order column. So first we will write one Raj, and then we will write the first order, that is muffin, and then we will write one Raj and then the second order, that is sugar. Same we will do for Riti, but since Riti is only having a single order, so we will write Riti only for once, 2 Riti muffin, and then Rahul is also having two orders, so we will write 3 Rahul sugar and 3 Rahul egg. So now here we can see that this particular column order, which was earlier holding multiple values, is now only holding single values. So we can say that the multi-valued attribute is eliminated and there are only single values which is present in this table. So we can say that this particular table is in first normal form. Now what would be the primary key in this particular table? So here you can see that for a given ID, the person name is getting repeated twice. For one there is Raj, again for one there is Raj. So we can't say ID and person name would be a primary key. Let's see that if ID and order can be a primary key or not. So here you can see that there is ID1 and then the order is muffin. Here there is ID1 and then the order name is sugar. So here we can see that there is no repetition. So we can say that ID and order combinedly act as a primary key for this particular table. Now let's see the second approach. So in the second approach, what we can do is, we can make new columns for each multi-value which is present. So consider here the order is having at max 2 values. So what we can do is, we can make different columns. First we can make it as order 1 and second we can make it as order 2, so that it can store all the values which is present in order. So we will make the table as ID, person name, then we will make the column as order 1 and then second column as order 2. So we will just fill the data. So for one Raj there is one time muffin and the order 2 is sugar. So we will fill one Raj muffin sugar. Then coming to Riti, so for Riti there is only one order. So in order 1 we will fill muffin. But since there is no order 2 or there are no 2 orders, we will be filling value as null. Null basically means empty. Now coming to the third, for Rahul there are also 2 orders. So for the first order we will be entering sugar and for the second order we will be entering egg. In this approach, if you see, according to the values which is present in the order, we are making new columns. But consider that if there are 9 orders which are present, would you be making 9 order column, order 1, order 2 till order 9? That is not a feasible case, because for each and every order you need to fill null as a value for Riti. There could be more person in this particular table who are having only one order. So for them also you need to fill null. So this is not an approach which is always suggested, but since you can see that this particular table there is no multi-valued attribute, so we can say that it has converted the table into first normal form, but this is not a suggested approach. Now coming to the primary key of this particular table, so we can see that ID is something which is unique for each and every order, each and every person. So the ID would be acting as a primary key here. Now coming to the final approach. In final approach, what we will do is we will divide the table into two tables. First is the student table and second is the order table. So we'll see that order is the multi-valued attribute. So what we will do is we will divide the table into two tables. First table would be having ID and person name. Second table would be having order, but we need to maintain that this particular order belongs to which particular person or which particular ID. So we will be breaking it into ID as well as order. So there would be two tables. First is having ID and person name, second is having ID and order. So we will break the table based on the multi-valued attribute. Now here you can see that there is ID and person name, and ID is unique for each person and ID can uniquely identify each person. So we can say that ID is acting as a primary key here. And here you can see that there is a relationship which is established between two tables, because this particular table tells me that corresponding particular ID is having which order, and here it tells us that what is the name of a person corresponding to their ID. So we can say that there is a relationship which is established, and this ID is taking reference from this particular ID which is present here. So we can say that this is a foreign key as it is taking reference from the base table. So we have divided the table into two tables, base table and the referencing table. In the base table, there is a primary key which is acting as a foreign key in the referencing table. Now here you can say that order is now having only single values. It is having all the IDs which is corresponding to the given order, and this particular table has now been converted into the first normal form. So this was the last approach which we can follow, and this is kind of a best approach which we can follow because we oftenly divide the table and we can say that the data redundancy is also less. Yes, I do agree that in this particular ID column we can see some of the duplicate entries, but in this particular table we are not seeing any duplicacy, and in this particular table ID and order both are acting as a primary key. So ID and order both can together help me identify unique values, and here ID can help me identify unique values. So there is some level of duplicacy because normalization doesn't guarantee to remove the entire duplicacy, but the duplicacy is reduced in comparison to this case. Now before starting with second normal form, let's just revise about first normal form. So according to first normal form, in a given table, there shouldn't be any multi-valued attribute. So basically there shouldn't be any column which can hold multiple values. The values should always be atomic. That is, there should be always a single value. There shouldn't be multi-valued attribute present in a given table. Now coming to the second normal form. So a relation is in second normal form if it satisfies the following conditions. So the first condition it should always be in first normal form, and the second condition is it should not have any partial dependency, which means no non-prime attribute is dependent on any part of candidate key. Now candidate key is basically a unique identifier which helps us to uniquely identify records in a table. What is non-prime attribute? So we learnt about prime attributes and non-prime attribute. So consider that in a given table there are three attributes A, B and C, and AB is our candidate key. So the attributes which are a part of candidate key lies in the prime attribute, and the attributes which are not a part of candidate key lies in the non-prime attribute. So according to this, there shouldn't be any non-prime attribute that is dependent on any part of a candidate key. Now here we learnt about this term partial dependency. So let's understand what partial dependency exactly is. So what is partial dependency and when a partial dependency is there in a table? So a partial dependency is there in a table when the LHS is a proper subset of candidate key and RHS is a non-prime attribute. So whenever you are given any question, you are provided with all the attributes which are present in the table, then you are provided with the functional dependencies, like this particular attribute is determining this attribute or B is determining C. So these kind of functional dependencies are present in our table. Now according to partial dependency definition, we have to see if LHS is a proper subset of candidate key and RHS is a non-prime attribute. If these exist, then we can say that our table is not in second normal form because there is a partial dependency. So as the term suggests partial dependency, you can understand it in this way that a particular non-prime attribute is partially dependent on candidate key because it says a proper subset. So if a proper subset of AB is to be considered, so it will be A and B. it won't include AB in the set because that is a subset, not a proper set. So whenever we talk about proper subset, it will only contain A and B and not AB. So whenever there is a partial dependency, a part of candidate key is determining a non-prime attribute. So since a part of candidate key is determining, we can say that there is a partial dependency. Because a part is determining, there is a dependency, and there is a non-prime attribute which is getting partially determined. So we'll see about partial dependency in the next set of slides, but right now you can conclude that if a given table is not in first normal form, also if there is some partial dependency, we can say that the given table is not in second normal form. So what is a non-prime attribute? As I told, that non-prime attribute is an attribute that is not part of a candidate key. Now here you can see that there is a table. In this particular table, we have customer ID, we have order ID, and we have order name. So we have order ID, and according to the order ID, we have the order name. And here we have the customer ID of a customer who has placed this particular order. Now coming to this particular table, we have a candidate key as customer ID and order ID combination. So prime attribute would be the one which is a part of candidate key, that is customer ID and order ID. And since now order name is left, so order name will come in non-prime attribute because it is not a part of candidate key. So in this relation, you can see that order name is somehow dependent on order ID for its value. So if order ID is 1, the order name is muffin. If order ID is 2, the order name is sugar. So order name is somehow dependent only on the order ID. It's not dependent on the customer ID, because if I know the customer ID, I can't say the order name before even knowing the order ID. So because of that, the order name is having a dependency on order ID. But here we told that customer ID and order ID both are acting as a candidate key. And here a part of candidate key is determining a non-prime attribute. So we can say that there is a partial dependency. So according to order ID, we provide the order name, and order name is determined only by order ID. And here customer ID, order ID together are acting as a candidate key, but here only part of candidate key is determining the non-prime attribute. So we can say that there is a partial dependency. This particular table is not in second normal form. So how can we make the table in second normal form, or how can we normalize the table? So as I told, that normalization is basically breaking of tables into 2 or more subtables, or you can say decomposition of table into 2 or more subtables, so that the duplicacy or data redundancy is reduced. Also the data is consistent. So what we will do is we will divide this particular table into 2 tables. So now the question which would be coming to your mind is how we will even divide this table. What all attributes should be there in the first table, in the second table, or if there are 3 tables, how to divide this particular table. So what you can do is, firstly let's consider this table. So let's name the table as A, here the table is B, and here the table is C. Now in A, the candidate key is customer ID plus order ID, and we have order name which is kind of dependent on order ID. So if we know the order ID, we can get the order name. So what we will do is, we can see that order ID is something which is common between the non-prime attribute and the candidate key. So we will break the table on the basis of order ID, and we will try to have order ID in the next table as well, because in this way we won't lose the track of which particular customer has ordered which particular order. So we will divide the table into 2 or more subtables, and here the table is divided into B and C, and here the table is having customer ID and order ID, and here the table is having order ID and order name. So corresponding to the order ID, we have the order name, and here the customer ID has the order ID corresponding to which we can get the order name from the second table. Now here, can you see that in this particular table, we have the candidate key, that is customer ID plus order ID. But coming to this particular table, what should be the candidate key here? So here you can see that order ID is also getting repeated, order name is also getting repeated. So can we say that order ID and order name combined would be a candidate key? Yes, we can say that. So we will have order ID as well as order name combinedly as a candidate key. So now you can see that when the table is divided into 2 or more subtables, we have seen that now order name is directly dependent on order ID. There is no other candidate key which is present. And this is also a prime attribute. This is not a non-prime attribute, because right now this is also a part of candidate key. So we can say that now there is no non-prime attribute which is getting determined by a part of candidate key. So in this way we can normalize the table. Now coming here, you can see that order ID is present here, and in this table as well, in table B and in table C. Now here you can see that there is a relationship which is established. So here the customer tells that this particular order ID I have ordered, give me the order name. So you can see that there is a relationship between two tables which is being established, and it is established on the basis of order ID. So this particular order ID is taking reference from this table, that is B table. So we can say that order ID here is acting as a foreign key which is helping me to establish the relationship between these two tables. So let's solve a practice question in which we will be provided with some attributes, we will be provided with some functional dependency, and we have to say that if the given table is in second normal form or not. So let's see. So consider that there is a relation R which is having A, B, C, D as attributes. The functional dependencies which are provided are AB determines C, AB determines D, and B determines C. Now in this relation, find if this is in second normal form or not. So let's see what we will do. So the very first step is we will identify the candidate key in this given relation. So how to find the candidate key we have already discussed in one of our videos. So you can go ahead and watch it and then come to this video. So for candidate key, what we will do is firstly we will list down all the attributes which is present in our table. Secondly, what we will do is we will check for all the dependents if the determinants are present here. If it's present, then we will discard the dependents. So here the dependent is C. C is already present. So AB is the determinant. So we can discard C. Now it's ABD. Now coming to the next functional dependency, D is present here, and since AB is already present here, we can discard D. So now coming to the next functional dependency, here C is the dependent and B is the determinant. But since dependent is not present, we can't discard B. So at the last, we are left with AB. So what we will do is we will take the closure of AB and we will see that if it's determining all the attributes which is present in our table. So A can determine itself. B can determine itself from the property of reflexivity. B can also determine C, so we can write C. AB can also determine D, so we can write D. So AB can determine all the attributes which is present in our table. So we can say that AB is a candidate key and we can add it in the prime attributes. Now in the next step, there could be more candidate key. So for that, what we will do is, we will see that if AB is lying in any of the RHS, because if AB is someone's dependent and there is a determinant which can determine AB, we can replace AB with that, or ideally A or B with that. So let's see if A, B or AB is present in the RHS. So here it is C, here it is D, here it is C. So there is no A, B or AB present in the RHS, so we can say that there will be only one candidate key for this particular table, and that is AB. Now here we have found out that AB is the candidate key here. The step 2, we will check for the partial dependency to tell that if this given table is in second normal form or not. So for that, there should be two rules which should be followed. So first is LHS should be a proper subset of candidate key, and here we have found out that AB is the candidate key. So if we take the proper subset, we get A and B. So we have to check that if LHS is a proper subset of candidate key in a given functional dependency, and if RHS is a non-prime attribute. So since AB is a candidate key, we can say that AB lies in the prime attribute, and the rest attribute which is not a part of candidate key, we can say it lies in the non-prime attribute, that is CD. If these two exist, we can say that there is a partial dependency and table is not in second normal form. But if none of the dependency is having any partial dependency, we can say the table is in second normal form. So these were the functional dependency which were provided to us. This is the candidate key, that is AB. So the prime attributes are AB, the non-prime attributes are CD. So let's check for the first functional dependency. So we have to first check if LHS is a proper subset of candidate key or not. So AB is a candidate key, but there is no proper subset. Proper subset of AB is A and B, but it is combinedly present. So since there is no proper subset and since there is an AND condition, so we won't check for the second condition. AB is not a proper subset, it is a subset of AB. So we can say that this particular functional dependency doesn't have any partial dependency. Now coming to the second functional dependency, so again you can see that there is AB present. So there is not a proper subset of AB which is present, subset of AB is present. So we can also say that this particular dependency is also not having any partial dependency. So coming to the third functional dependency, that is B determines C. So here in the LHS you can say that B is a subset of AB, or you can say that B is a subset of candidate key. And according to these rules, if LHS is a subset of candidate key, we need to check for the second rule, and if second second rule also applies. There is a partial dependency. So we'll check for RHS, and RHS is C, which is a non-prime attribute. And here, according to this rule, RHS is a non-prime attribute and LHS is a proper subset of candidate key. Then there is a partial dependency. So we can say that this particular dependency have some partial dependency, because of which this particular table is not in second normal form. So from this we can conclude that this particular table is not in second normal form. And also we have analyzed the dependency and we saw that one of the dependency was having some partial dependency. So that is why the table is not in second normal form. Now, according to the first normal form, there shouldn't be any multi-valued attribute, or there shouldn't be any attribute which has multiple values. According to second normal form, there shouldn't be any partial dependency which should exist in a table. Now let's see what third normal form says. So according to third normal form, it should be in second normal form, like the table should be in second normal form. Second is, it shouldn't have any transitive dependency, which means that no non-prime attribute should be transitively dependent on a candidate key. So what is this transitive dependency? So transitive dependency occurs when non-prime attribute is dependent on another non-prime attribute. So whenever there is a non-prime to non-prime dependency, we can say that there is a transitive dependency. Let's understand transitive dependency in more depth. So consider that I have been given a project. Now for that particular project, I need some details, I need some books. So I'll go to a library A. Now that particular library borrows book from library B. So somehow you can say that for my project X, I want some books from library A, but library A is somehow borrowing some books from library B. So library A is dependent on B for the books and I am dependent on library A for the books. So you can see that there is some transitive dependency which I am having with library B, because if the books are not present in library B, it will not reach to library A, and if it doesn't reaches to library A, I won't be getting that books. So this is called a transitive dependency, when I'm not directly dependent on something but indirectly dependent on something. So in this way we can say a partial dependency or a transitive dependency occurs in a table, and whenever there is a transitive dependency in a table, we can say that that particular table is not in third normal form. Now, there are two ways in which we can determine if a given functional dependency is following the third normal form or not. So if there is a transitive dependency, there would be a non-prime to non-prime dependency. Also, if we want to check that if there is no transitive dependency, so we can check for these two rules. That is, if X is determining Y is a functional dependency, then either X should be a super key or candidate key, or Y should be a prime attribute that is a part of candidate key. So if any one of these holds true, we can say that this functional dependency doesn't have any transitive dependency. So if there is no transitive dependency, X will always be a part of super key or candidate key and Y will always be a prime attribute, because consider that here X is determining Y and consider that Y is determining some Z, and since Y is a prime attribute and using the rule of transitivity, we can say that X will determine Z. So X is determining Z using a prime attribute. There shouldn't be any case where Y is a non-prime attribute and using that non-prime attribute X is getting determined by Z. So this determining factor should always be a prime attribute, or we can say for the rule of transitivity to exist, the dependent should always be a prime attribute, and since X is determining Y, X should always be a part of candidate key or a super key. I know this might sound confusing, but now you can remember it in this way, that there shouldn't be any transitive dependency in the given table or in the given functional dependency, and how we can identify that there shouldn't be any non-prime to non-prime dependency, that if X determines Y is there as a functional dependency, X and Y both shouldn't be non-prime attributes. Either X should be a candidate key or super key, or Y should always be a prime attribute. So let's understand from an example. Consider that there is a relation ABCD with functional dependency AB determines C and C determines D. Find if it is in third normal form or not. So we need to check that if there is any transitive dependency. And for the transitive dependency check, we need to know that for this particular table, what are the non-prime attributes. So finding the non-prime attributes is very easy when we know the candidate, because all the attributes which are not part of candidate key lies in the non-prime attribute. So let's find the candidate key for this given table. So firstly what we'll do is we will note down all the attributes which is present in our table. Then we will check that for a given dependent if its determinant is present and dependent is present or not. If its determinant is present, we can discard the dependent. So here we can see that C is the dependent and AB is the determinant. C is already present here, and if we have AB, it can always determine C. So we can discard C from here. So for the next functional dependency, we can see that D is present, D is the dependent and C is its determinant. So if the dependent is present, we can discard the determinant. But since C is not present here, we can't discard anything. But if you see closely to this functional dependency, it says that AB determines C and C determines D. So can we say that AB will determine D using the rule of transitivity? So we can say that if AB is present, it can already determine D. So if AB is present, it can already determine D. So we can discard this as well. So now we are left with AB. Now we need to take the closure of AB to see if it determines all the attribute which is present in our table. So A can determine itself, B can determine itself, AB will determine C, and C will determine D. So we can say that AB is a candidate key. Now we need to see that if any of this A or B is present in the right hand side of any of the functional dependency. If it's present, we can replace and find out more candidate key. If it's not present, then we can say that this is the only candidate key. So let's see. So in the right hand side of the first functional dependency, it's C. In the right hand side, it's D. So we can say that there won't be any more candidate key. So AB is a candidate key here. So we can say that AB is a candidate key here. Now in the next step, we need to check for the transitive dependency. If there is any transitive dependency, we can say that the given table is not in third normal form. If there are none of the transitive dependency, we can say that the given table is in third normal form only if the table is in second and the first normal form. So always keep this thing in mind that for a table to be in third normal form, it should always be in second normal form. If it's not in second normal form, we can't even say that the table is in third normal form. So from here we have find out that AB is the candidate key. Let's find the prime and the non-prime attribute. So prime attributes are the one which are the part of candidate key, that is AB, and non-prime are the one which are not a part of candidate key, that is CD. So in this particular table, we have found out the candidate key, we have found out the prime attribute, and we have found out the non-prime attribute. Now let's see that if there is any non-prime to non-prime dependency existing in the table or not. So there are two functional dependency. For the first functional dependency, AB determines C. So is AB a non-prime attribute? No, neither of A nor of B are a non-prime attribute. And is C a non-prime attribute? Yes, C is a non-prime attribute, but since AB is not a non-prime attribute, we can say that there is no transitive dependency as AB is a candidate key or a super key. Now coming to the next functional dependency, C determines D. Now here C is a part of non-prime attribute. So the first condition is agreeing that there shouldn't be any non-prime attribute in LHS. Now coming to RHS, D is also a part of non-prime attribute. So RHS is also having a non-prime attribute. So there is a non-prime attribute which is determining a non-prime attribute. So we can say a transitive dependency is existing because C is not a super key or candidate key, or D is a prime attribute and a non-prime to non-prime dependency is existing where a non-prime attribute is determining a non-prime attribute. See, prime attribute can determine a non-prime attribute, non-prime attribute can determine a prime attribute can also determine a prime attribute, but there shouldn't be any dependency where a non-prime attribute is determining a non-prime attribute. So till now we have discussed on this non-prime to non-prime dependency, but do you even wonder that why this particular dependency, if exists in a table, we say that table is not in third normal form. So consider an example that there is a table. Now in this particular table, we oftenly find the primary key or the candidate key because that act as a unique identifier. So consider that there are three columns A, B and C. So here A is acting as a key, either you can say primary key or candidate key. Now why do we even need key in a table? So basically key help us to uniquely identify records in a table. If I know the value of A, I can tell the value of B and C. But consider that there is a case where I know the value of B. Would I be able to tell the value of C or A? Consider that here the value of B is 1 and 1 and here the value of C is 4 and 5. So if I tell you that the value of B is 1, tell me the value of C. So if you look here, for 1 it is also having the value as 4, for 1 it is also having the value as 5. So would the value of B help me to find the value of C? No, it would not help me, right? So for that purpose only we have a key. We can say candidate key, super key, primary key in a given table, so that we can uniquely identify our records. If I know the value of A, I can tell the value of B and C for that particular value of A. So for that particular purpose, we have a candidate key. And when there is no candidate key or no prime attribute or super key which is determining something, we can say that we won't be able to determine anything, because now the dependent values can be different. So for the dependent values to remain same, we need to have a candidate key or super key as a determinant, because it will help me to identify the values. So that is why there shouldn't be any non-prime to non-prime dependency, because there should always be a determinant which should be a candidate key which can help me to find the value of dependent. So the very first question which would be coming to your mind is, why do we even need to learn about Boyce code normal form if we have already learnt about third normal form? And you are saying that this is a refinement to the third normal form. So what was the issue in third normal form? So if you remember, according to third normal form, if there is a dependency X determines Y, X should either be a super key or a candidate key, or Y can be a prime attribute. So because of this OR, we were encountering some anomalies and some data redundancy. Let me explain you why. So consider there is a relation R which is having attributes as A, B, X and Y. In this particular relation R, B and Y are prime attributes and X is a candidate key. So consider there are two functional dependency, X determines Y, A determines B. So in this, since X is a candidate key, we can say that it follows the third normal form rule. So this particular functional dependency is in third normal form. Now coming to this dependency, here A is neither a candidate key or super key, but here B is a prime attribute. So because of this, we can say that this particular functional dependency also follows the third normal form rule. But here A wasn't a candidate key or super key, because of which there was some data redundancy or duplicacy which was there, and it was causing some certain anomalies to be present in our table. Now because of that, the Boyce code normal form was introduced so that we can add some refinement to the third normal form. Now according to Boyce code normal form or BCNF, a relation should be in third normal form. Second, for a given functional dependency X determines Y, X should always be a candidate key or super key and should only determine non-prime attributes. So according to the Boyce code normal form, it says that there shouldn't be any OR condition. X or the determinant should always be a candidate key or super key, so that there is no data redundancy or the data redundancy is reduced. So let's understand from an example. Consider that there is a relation R which is having attributes as A, B, C and D, and there are some functional dependencies which are provided. So find if this particular relation is in BCNF or not. So what we will do is, first we will identify the candidate key. So let me just write down all the attributes which is present in our table, and then we will see if the dependent is present here or not, and if its determinant is also present here or not. If it's present, then we can discard the dependent. So C is the dependent and its determinant is AB. So since C is present, AB can determine C, so we can discard C. Now ABD is present. Now coming to this functional dependency, D is the dependent and AB is the determinant. D is also present and AB is also present. So we can discard the dependent, and now AB is present. Now there are no functional dependencies, so what we will do is we will take a closure of AB. So it will give me A, B, C and D. And there is no proper subset of AB which will give me all the attributes. So I can say that AB is a candidate key. So AB is the candidate key here. Now as part of second step, we have to check for the candidate key or super key in LHS. So these are the functional dependencies. So coming to the first functional dependency, since AB is the candidate key and AB determines C, we can say that LHS AB is a candidate key, so it follows the Boyce code normal form. Now coming to the second functional dependency, that is AB determines C, since again AB is a candidate key, so this also follows the BCNF rule. So we can say that this particular relation is in BCNF. Let's just re-revise some older concepts and then we will switch to the decomposition. So consider there is a relation R. Now this particular relation R has some rows, has some columns and has some data present in it. Consider that there is a data redundancy, or you can say data duplicacy, which is present in this particular table or this particular relation. So what we will do is we will normalize the relation. So what we do in normalization is we break or decompose the given relation into two or more sub-relation so that the data redundancy or data duplicacy is decreased. So we have broken it into R1 and R2. Now this particular decomposition can be of two types. First is a lossy decomposition and second one is a lossless decomposition, which we will be knowing in this particular video. So in normalization, we generally break or decompose the table into 2 or more subtables. Now consider if there is a relation R, lossy decomposition occurs when a relation R is decomposed or broken into 2 or more relation, but the data is lost. So basically in this kind of decomposition, the data is lost and the original relation R can't be reconstructed by joining these decomposed relation. So if there is a relation R which is broken or decomposed into R1 and R2, and consider that if I want to find some data which is present in R1 as well as R2, I perform a join operation between them, and after performing the join operation I get R3. So according to the definition of lossy decomposition, R3 would never be equal to R, which was our base table. So some data is lost and some data may be repeated as well. So the data which is present in R3 is not equal to the data which is present in R. Basically data is not preserved. So there are two rules for decomposition to be lossy. The first rule is some data from the original relation R is lost after decomposition. So R3 is not equal to R. Second is join of the decomposed relation R1, R2 till Rn, if there are n number of relation, is not equal to the original relation R. So after getting decomposed and performing the join operation, the resulting relation is not equal to the base relation, or you can say the relation R, which was the original table. So let's understand lossy decomposition from an example. So consider that there is a relation R which is having attributes as A, B and C. So this is the relation R which is having attributes A, B and C. So what we will do in step 1 is we will decompose the relation based on any attribute. So we can choose any attribute and we can decompose the table based on that attribute. Consider that we are choosing B. So we'll decompose the table into AB and BC. So for now, let's use B as the common attribute. Decomposed relations are R1, R2. R1 is having A and B and R2 is having B and C, and the value remains the same. So A is 1 and 4, A is 1 and 4, B is 2 and 2, C is 3 and 6. So all the values remain the same. It's just that we have broken the table vertically from B, and B is the common attribute which is in the relation 1 as well as in the relation 2. Now step 2 is let's perform a natural join between R1 and R2. So what is this natural join? Join is basically a cross product plus some condition. So whenever we perform a cross product and then we provide some condition and on basis of that we filter the data, we perform join. Now coming to the natural join. So what happens in natural join is we do the cross product, and then the condition in natural join is that the attribute which is present in relation 1 should be equal to the attribute which is present in relation 2. So on basis of this, we will filter out the data. So let's perform a natural join between R1 and R2. So what we will do is first we will do a cross product. So for the cross product, the first row of R1 will be cross product with both the rows of R2. Then the second row of R1 will be cross product with both the rows of R2. And then we will filter the data based on the condition. So what we will do is first we will note down the values of R1, that is 1 and 2. Now 1 and 2 will be cross product with 2 and 3 of R2. And then 1 and 2 will again be cross product with 2 and 6. Now coming to 4 and 2. So 4 and 2 will be cross product with 2 and 3. And again 4 and 2 will be cross product with 2 and 6. Now what we will do is we will follow the condition that the common attribute should be equal. So R1 of B should be equal to R2 of B. So this is AB and this is BC. So let's see if R1 of B is equal to R2 of B. Yes. So this will be in our final result. Coming to this, R1 of B is equal to R2 of B. Yes. So this will also be in our final result. Coming to third, R1 of B is equal to R2 of B. Yes, so it will be also displayed in final result. Coming to the last one, R1 of B is equal to R2 of B. Yes, so this will also be displayed in the final result. So the final relation we will get after the join is 1, 2, 3, 1, 2, 6, 4, 2, 3 and 4, 2, 6. Now this was our original relation which has 1, 2, 3, 4, 5, 6. And this is the relation after we perform the natural join. So here you can see 1, 2, 3. Which is present here as well, but coming to 4, 5, 6, it is not present here. So we can see that data is lost, and we can also see some additional fields which is present here. So we can clearly say that R3 is not equal to R because some data is also lost and some extra data is present. So this is a lossy decomposition. So we saw in the lossy decomposition that our data was also lost and there was some extra set of data which was also present. But now we have to make sure that even if the decomposition happens, the data is not lost. So that is a lossless decomposition. So whenever we see a lossless decomposition, it basically means whenever the decomposition happens and if there is a join operation which is performed between both of these relations or the decomposed relation, we don't lose the data. The data is preserved. So let's see that how we can ensure that the decomposition is a lossless decomposition. So the first pointer is divide or decompose the table on the basis of candidate key or super key present in the relation so that there is no duplicacy. So as we can also see that in the lossy decomposition there was some duplicacy, there was some extra data which was present. So we have to make sure the attribute on basis of which we are dividing the table should either be a candidate key or should be a super key, so that this unique identifier will help me to eliminate the duplicate data. Now coming to the second pointer, for a decomposition to be lossless, first is R1 union R2 should be equal to R. So whenever we do a union between the decomposed table, it should always result into the original table. Now the second one is R1 intersection R2 should be equal to the common attribute. So consider if our relation is broken down into R1 and R2, and R1 is having AB as the attribute and R2 is having BC as the attribute. So whenever we do an intersection between them, it should result into the common attribute which is present between this relation. So R1 intersection R2 should result into the common attribute. Third pointer is to ensure that a decomposition is lossless, a common approach is to use the dependency preservation property. Now we will learn about this dependency preservation property in next set of videos, but for now you can keep these two pointers in mind so that a decomposition is not lossy, it's lossless. Now coming to the lossless decomposition. So consider that there is a relation R. So in lossless decomposition, it ensures that when a relation R is decomposed or breaked into two or more relations, no data is lost. That is, the original relation R can be again reconstructed by joining these decomposed relations. So if there is a relation R which is decomposed into R1 and R2, and whenever we perform a natural join or a join between them, if we get R3, so the data which is present in R is equal to the data which is present in R3. So the data is preserved and we get the original table after performing the join operation. So there are two rules for a decomposition to be lossless. First one is all data in the original relation R should be preserved after decomposition, and second is join of the decomposed relations is equal to the original relation. So let's understand from an example for the lossless decomposition. So consider there is a relation R having attributes as A, B and C, and the candidate key here is given as A. So what we will do in the lossless decomposition is we will divide the table on the basis of the candidate key, and that would be a common attribute. So let's decompose the relation based on the candidate key or super key of given relation. So the decomposed relation would be R1 which will be having A and B, and R2 which would be having A and C. Since A is the super key or candidate key, so this would be a common attribute. Now these are the relations R1 and R2. So let's perform a natural join between them. Now whenever we perform a natural join between two relations, what we do is we do the cross product among two relations and then we perform a condition between them, that is the common attribute in R1 should be equal to the common attribute in R2. So first we'll do the cross product. So first this row will be multiplied with all these rows. So 1, 2 is multiplied with 1, 3. Then again 1, 2 is multiplied with 4 and 6. Now coming to the second row. So 4 and 5 will be cross product with 1 and 3. And then again 4 and 5 will be cross product with 4 and 6. Now let's check for this condition where R1 of A should be equal to R2 of A. So this is R1 of A and this is R2 of A. So R1 of A is equal to R2 of A. Yes. So 1, 2, 1, 3 will be in the final result. R1 of A is equal to R2 of A. No. So this should be discarded from the final result. R1 of A is equal to R2 of A. No. So this should also be discarded from the final result. R1 of A is equal to R2 of A. Yes. This should be present in the final result. So if you see the original relation, it has 1, 2, 3, 4, 5, 6, and if you see the relation after natural join, it also has 1, 2 and 3 and 4, 5 and 6. So the relation which we get after performing a natural join on the table is same as the original relation. So in step 2, let's perform a natural join between R1 and R2, and whenever we do R1 natural join R2, we get the original relation back. So consider this is a relation R3. So R3 is equal to R because all the data which is present in R is present in R3. So that is why this is a lossless decomposition. As the word suggests, dependency preserving decomposition. So whenever we are having decomposition or whenever we are in a process of having decomposition, if the functional dependency before the decomposition and after the decomposition are preserved or maintained, we call it as dependency preserving decomposition. So dependency preserving decomposition ensures that the functional dependencies are preserved or maintained after decomposing a relation into two or more smaller relations. So it makes sure that the functional dependencies are preserved before the decomposition as well as after the decomposition. Now here consider an example. So consider a relation R which is having attributes as A, B and C with functional dependencies as A determine B and B determine C. Find its dependency preserving when it's divided into relation R1 which is having A and B and relation R2 which is having B and C as the attribute. So here we have a relation ABC which is now divided into two relation R1 and R2 where R1 is having AB as the attributes and R2 is having BC as the attribute. Now we have to see the functional dependency which was there before the division or before the decomposition is preserved or maintained or not. Now coming to the first relation, that is R1. So it is having attributes as A and B. Now if we want to form a functional dependency using these attributes, what can we form is A can determine itself, B can also determine itself. These are trivial dependency. Or we can say the property of reflexivity. Now A can also determine B. These functional dependency we have derived. Now coming to the trivial dependency, we generally don't care about trivial dependency because it always holds true. So for this we don't need to look at. Now coming to these, is there any functional dependency which is present here which is also here? So we can see that A determines B is there before the decomposition and A determine B is also there after the decomposition. So we can say that this particular functional dependency is preserved using this particular decomposition table. Now coming to the second table, that is R2 which is having attributes as B and C. So the trivial dependencies could be B determine B, C determine C, but we don't need to take care of trivial dependency. So coming to the non-trivial one, so it could be B determine C. So among these functional dependency, let's see if there is any dependency which is preserved even after decomposition. So you can see B determine C is here as well and here as well. So before and after the decomposition, B determines C is preserved. So in this particular table BC, B determines C is preserved. So both of the functional dependencies is preserved. So we can say that the decomposition is dependency preserving because the functional dependency A determine B and B determine C are preserved in relations R1 and R2. Now let's see one more example so that the concept is clear. So consider there is a relation R which is having attributes as A, B, C, D and the functional dependencies are A determine B, A determine C, C determine D. Find if it's dependency preserving when divided into R1 ABC and R2 CD. Coming to the first relation, that is R1 which is having attributes as A, B and C. So since this R1 is having attributes as A, B and C, there could be some functional dependencies which would be present. So first what we will do is we'll take the closure of A. So if we take the closure of A, it will give me A, B, C and D, all the attributes. Coming to the closure of B, it will only give me B. Coming to the closure of C, it will give me C and D. So from here we can say that A can determine A can determine B, A can determine C, A can determine D. So we can make the functional dependency as A determine B and A determine C. Now coming to B, B can only determine itself, so we will discard it. Coming to C, so C can determine itself and C can determine D, but there is no D present in this particular relation. So these two would be the functional dependencies which would be for this particular relation. And coming to the functional dependency which was present before, so we can say that A determine B is a functional dependency which is preserved here. Coming to A determine C is also a functional dependency which is preserved here. So we can say that for the first table A, B, C, A determine B and A determine C is preserved. Now coming to the second table, that is R2 which is having C and D. Now from C and D, C can determine C and C can determine D. So there would be only one functional dependency, C determine D. And now if we see to the functional dependency which was present before the decomposition, there is a C determine D, and after decomposition also C determine D is there. So C determine D is also preserved. So the decomposition is dependency preserving because the functional dependency A determine B and B determine C are preserved in R1 and R2. So if you want to find that if a given relation is having dependency preserving decomposition or not, what you can do is you can note down the relation and then you can find out the decomposed table of that particular relation. For the original relation, you can note down the functional dependency. For the decomposed relation, you can find out the functional dependency using the closure method, where you can find the closure of individual attributes, and when you find the closure of individual attributes, you can know which all attributes that particular closure can define, and then you can derive some functional dependency based on that. Once you have derived the functional dependency, you need to check if the functional dependency which is derived after decomposition and if the one which was present before decomposition is preserved or not. In this way, you can find out if a given relation or if a given functional dependency is dependency preserving or not. Now, what is fourth normal form? So, a relation is said to be in fourth normal form if it satisfies the following condition. So, the first condition is it should be in BCNF, that is Boyce code normal form. Second is it shouldn't have any multi-valued dependency. Now, what is this multi-valued dependency? So, a multi-valued dependency, x determines y, x determines z, in a relation R, xyz implies that for each value of x, there are a set of values of y and set of values of z that are independent of each other. So, according to multi-valued dependency, if x is having a multi-valued dependency on y, so for every value of x, there would be multiple values of y. Or if x is having a multi-valued dependency on z, so for every value of x, there would be multiple value of z. So, let's understand from an example. Consider that there is a relation student which is having student ID, student course and student phone number. Now, one particular student can have multiple course, one particular student can also have multiple phone numbers. So, let's see from this relation. So, here you can see that the student ID is 1, but the course he has taken is maths and the phone number is 123. Again, the student ID is 1, the course he has taken is science and the phone number is 123. Now, again coming to the student ID is 1, the course he has taken is maths, but now the phone number is 345. So, we can say for a student ID 1, the course is maths and science and the phone number is 123 and 345. So, you can see for a given student ID, we are providing 4 entries. Now, again coming to student 2, so student 2 has taken Hindi and English and the phone numbers are 678 and 910. So, here you can see that there is so much of redundant data. So, let's see that how we can decompose the table and get rid of this redundant data. So, this was our base table or original table. Now, it has been split into 2 tables. And the common attribute between them is student ID. So, what we have done is we have split the table into student ID and course and then student ID and phone number. Now, here you can see that student ID is only having 2 entries and the course is mentioned for that particular student ID. And now coming to the second table, it has happened in the same way that the student ID is now mentioned only 2 times and the phone number corresponding to the student ID is mentioned. So, you can say that the data redundancy or data duplicacy is reduced here, and since we have decomposed the table, we have often normalized the table. So, this now fifth normal form, or we can also call this project joint normal form, that is PJNF. So, a relation is said to be in fifth normal form if it satisfies the following condition. First is it should be in fourth normal form. Second is the decomposition should be lossless. Now, what is this lossless and lossy decomposition? So, we have already learned about lossy and lossless decomposition in last set of videos. You can go ahead and have a look. But just to re-revise, let's have a look again. So, consider that there is a relation. Now, this particular relation have some redundant data. So, according to normalization, we normalize or we decompose the table into 2 or more subtables so that the data redundancy is less. Now, this particular decomposition of relation can be of 2 types, lossy and lossless. Now, in lossy decomposition, we often lose the data or data is lost or data is not preserved, and in lossless decomposition, the data is preserved even after decomposition. So, data is preserved. So, consider that if we have divided the relation or decomposed the relation into R1 and R2, and if we are performing a join operation between R1 and R2, which is giving me R3, so according to lossless, R3 would be equal to the original relation, that is R. So, all the data which is in R3 would be equal to the original relation. But in lossy decomposition, R3 wouldn't be equal to R, because in lossy decomposition, we often lost the data. So, the decomposition should be lossless for a relation to be in fifth normal form. Now, lossless decomposition, it ensures that when a relation R is decomposed or break into 2 or more relation, no data is lost, and the original relation R can be again reconstructed by joining this decomposed relation, that is R3 is equal to R for the lossless decomposition. Let's understand from an example. So consider that there is a relation R which is having attributes as A, B and C, and the candidate key is A. So often in lossless decomposition, we decompose the table on the basis of candidate key and make it as a common attribute between both the decomposed relations. So step 1 is, let's decompose the relation based on the candidate key or super key of the given relation. So decomposed relation are R1 AB and R2 AC. So this was our original relation which has A, B and C, and now it's decomposed to A, B and AC. Now whenever we perform a natural join between R1 and R2, so natural join is basically a cross product plus some condition. The condition is the common attribute in R1 should be equal to the common attribute in R2, on basis of which we have divided the table or we have decomposed the table. So after doing a natural join, we see that R3, or you can say R1 natural join R2 is same as the original relation. So all the data 1, 2, 3, 4, 5, 6 is preserved in this particular relation as well. So step 2, let's perform a natural join between R1 and R2. And whenever we do a R1 natural join R2, we get the original relation back, that is lossless. So we can say that this particular table or this particular relation is in fifth normal form because the decomposition is lossless, and it is also in fourth normal form. So how to find the highest normal form of a given relation? So the step 1 is, we have to identify the candidate key for the given relation using the functional dependencies which are present and the closure method. Now the step 2 is, we have to find the prime and non-prime attributes for the given relation. So prime are basically the ones which are part of candidate key, and non-prime are the ones which are not the part of candidate key. Now the step 3 is, we have to check for the normal forms one by one according to their rules. So all the normal forms have some specific rules. We have to see that if the functional dependency corresponds to the given rule or not. Now here you can see that there is a box which I have drawn. First is first normal form, second is 2NF, third is third normal form, and fourth one is BCNF. So it says that if a given relation is in BCNF, it is always in third normal form, second normal form and first normal form. If a given relation is in third normal form, it will always be in second and first normal form. If a given relation is in second normal form, it will always be in first normal form. And if a given relation is in first normal form, then it's in first normal form. So if any relation is present, if we check if the given relation is in BCNF or Boyce code normal form, we can say that it is in third normal form, second normal form and first normal form. If a given relation is in third normal form, we can say it is in second and first. If a given relation is in second normal form, we can say it is in first normal form. So this is the box, or this is the pattern which it follows. If a given relation is in BCNF, we can say that it follows all the three normal forms. So let's find out that how we can find the highest normal form for a given relation using this problem statement. Generally, we should start with BCNF, because if a given relation is in BCNF, we can say that it is in third normal form, it is in second normal form, and it is in first normal form. So if we start with BCNF, it would be very easy task. If we start with finding the first normal form, then we need to find the second, third and fourth as well. But if we start with BCNF, and if a given relation is in BCNF, we can say that it is in third, second as well as first. But here I'll be starting with finding the first normal form, second, third and BCNF, because I want to explain about each and every normal form. But whenever you get question, always start with BCNF so that you can find out that if a given relation is in BCNF or not. If it fails, then go for third normal form. If it also fails, then go for second, and if it also fails, then go for first. But it's better to start with the highest normal form. So let's start. So the first step is, we have to find the candidate key for the given relation. So to find the candidate key, first we note down all the attributes which is present in our table. Then we iterate to the functional dependency and we check if the dependent and determinant is present. If both of dependent and determinant is present here, we can discard the dependent because it can eventually be determined. So BC is the dependent and A is the determinant. Both are present, so we can discard BC. So we are left with A. Now coming to this functional dependency, C is the dependent, B is the determinant, neither of them is present. Coming to this, B is the dependent, A is the determinant, A is present but B is not present, so we can ignore this. Now coming to this, AB is the determinant, C is the dependent, A is present but B and C are not present. Coming to this, A is the dependent and B is the determinant, A is present but B is not present. So A is a possible candidate key. So let me find the closure of A. So closure of A gives me A provides me A, then A gives me B, then A gives me C, And then, okay, so A, B, C are all the attributes which are present in our table. So A closure give me all the attributes which are present in our table. Now we have to see that if A lies in the right hand side of any of the functional dependency, so we can see that A lies here. So we have to take the closure of B as well, because it could also be a possible candidate key. So let me find the B closure. So B can determine itself, B can determine C, and B can also determine A. So B closure can also determine all the attributes, and proper subset of them are neither a super key or a candidate key. So we can say that A and B are candidate keys. So candidate key here are A and B. Now in the second step, we have to find the prime and non-prime attributes. Prime are the one which are the part of candidate key, so we'll mention A, B here. Non-prime are the one which are not the part of candidate key, that is C. Now third is we have to check for the normal forms one by one according to their rule. Again, I am reiterating that we should always start checking from the BCNF, because that is the highest normal form, and if a given relation is in BCNF, it is in third, second and first normal form. So always check from the highest normal form. Here I am starting with the lowest normal form because I want to discuss on each and every normal forms and show you that how we can say that a given relation is in given normal form. So let's start with the first normal form. So a relation is in first normal form if it contains only atomic values, that is there shouldn't be any multi-valued attributes, like a attribute which is having multiple values, you can say phone number. So if an attribute is having multiple values, we say that this particular relation is not in first normal form. But here, since we are using a standard relational model, so we can say that it is already in first normal form. Now coming to the second normal form. So second normal form, a relation is in second normal form if it is in first normal form, that is already true, and every non-prime attribute is fully functional dependent on every candidate key of the relation, that is there shouldn't be any partial dependency. And when partial dependency occurs, when LHS is a proper subset of candidate key and RHS is a non-prime attribute. So if this holds true, we can say that the given relation has partial dependency, so it's not in second normal form. So we have A and B as the candidate key. If we take the proper subset of A and B, that is 5, basically empty, because there is no proper subset of A and B. Now coming to the RHS is a non-prime attribute, so we know that C and D are the non-prime attributes. So let's check for each and every functional dependency. The very first one is A determines BC. Since A is a candidate key and not a part of candidate key, we can say there is no partial dependency, because if it fails here, we don't need to check for the second condition. Now coming to B determines C, B is also a candidate key, not a proper subset of candidate key, so no partial dependency. Coming to third, A is again a candidate key, so we don't need to check for the second condition. Coming to fourth, AB both are a candidate key, so no partial dependency, as AB is a combination of candidate key, it is acting as a super key. Now coming to B determine A, again B is a candidate key, it's not a proper subset of candidate key, so we can say there is no partial dependency. So we can say that the given relation is in second normal form. We didn't check for the second rule because the first rule was holding false for each and every functional dependency, and if there is a false and if we do AND with any of the false, it gives we false. Now coming to the third normal form. So a relation is in third normal form if it is in second normal form and there is no transitive dependency which is existing. So we have to check that if there is a relation X determines Y, X is a super key or a candidate key, or Y is a prime attribute. If this is true, we can say that the given relation is in third normal form. So this particular rule basically says there shouldn't be any transitive dependency. So let's check for each and every functional dependency. So here A determines BC. A is a candidate key, so no transitive dependency. B determines C. B is a candidate key, no transitive dependency. A determines B. A is a candidate key, no transitive dependency. AB determines C. So A and B both are candidate keys, and when we put A and B together, that is a super key, because candidate key is a minimal super key. So A and B together acts as a super key and X is a super key, so there is no transitive dependency here, as AB is the combination of candidate keys, it's super key. Now coming to B determine A, B is again a candidate key, so there is no transitive dependency. So we can say that this particular relation is also in third normal form. Now coming to the fourth one, that is BCNF. So a relation is told to be in BCNF if it follows the third normal form, and for every functional dependency X determines Y, X is super key or you can say candidate key. So let's see for each and every functional dependency. So A determine BC, A is a candidate key, so it is in BCNF. B determine C, B is a candidate key. A determine B, A is a candidate key. AB is a super key, and B determines A, B is a candidate key. So we can say that the given relation is in BCNF as well. So the highest normal form for the given relation is BCNF. So we have already learned about normalization, types of normal forms and much more things. Now let's see that how we can normalize a table. So in normalization, we generally break or decompose the table into 2 or more subtables. Now how would that decomposition happen? How would we know that we have to decompose the table and how we should decompose the table? So let's see the steps to normalize a table. So the very first step is we have to write down all the attributes of the table, candidate key, prime and non-prime attributes, and start analyzing with the functional dependency. So in the question, we would be provided with a relation and their functional dependency. We have to find out the candidate key, prime, non-prime attributes, and we have to start analyzing the functional dependency. So the second step is for the table to be in first normal form, table should have atomic, that is indivisible or you can say single values, and have a primary key. For the table to be in second normal form, there shouldn't be any partial dependency. So when partial dependency occurs is when LHS is a proper subset of candidate key and RHS is a non-prime attribute. This should be false for the table to be in second normal form. Now coming to the fourth step, that is for the table to be in third normal form, there shouldn't be any transitive dependency. That is LHS must be a candidate key or RHS should be a prime attribute that should be holding true. Now coming to the fifth step, for a table to be in BCNF, LHS must be a candidate key or super key. Now coming to the sixth step, if it fails at any of these steps like second, third, fourth and fifth, where we are finding about first, second, third and BCNF, then we have to decompose the table on a common attribute which is a candidate key so that the decomposition is lossless, that is data is not lost. So let's understand from a practice problem where we have provided a relation, we have been provided with a functional dependency, and we have to see that if the table is normalized or not. If the table is normalized, we will check for the higher normal forms. If it's not normalized, we will decompose it and then again check for the higher normal form. So we will check till BCNF that if the table is normalized or not. So the step 1 is we have to find the candidate key, prime attribute, non-prime attribute and start analyzing the functional dependency. So to find the candidate key, first we will note down all the attributes of the given relation. Then we will iterate with the functional dependency and we will see if the dependent and determinant are present or not. If both of them are present, then we can discard the dependent because it can be determined. So the first functional dependency is A determine B. B is the dependent and A is the determinant. Both are present, so we can discard the dependent. So now we are left with ACD. Now coming to the next functional dependency, B determines C. So C is the dependent and B is the determinant, but B is not present here, so we have to leave this functional dependency. Now coming to where C determines D. So D is also present here and C is also present here, so we can discard D. Now we are left with AC. So from here you can see that A determines B and B determines C. So can we say that A will also determine C from the rule of transitivity? So we can see that A determines C and A and C both are present here, so we can discard the dependent, that is C. So we are left with A, and if we take the closure of A, it will give me A, it will give me B, B will give me C and C will give me D. So we can say that A is a candidate key. And now we have to see that if A is present at the right hand side of any of the functional attributes. No, it's not present. So we can say that A is the candidate key. So here candidate key is A, prime attribute are the one which are part of candidate key, so A is here, and non-prime are the one which are not a part of candidate key, so that is BCD. So in step 2, since we have found out the candidate key, prime and non-prime attribute, we have to check for the first normal form. So since we are assuming that our relation is in standard relational model, it is already in first normal form. So here we can see all the values are atomic only because it is a standard relational model. Now coming to the step 3, that is we have to find for the second normal form. So to check for the second normal form, we have to check that if there is any partial dependency present or not. If it's present, then it's not in second normal form. If it's not present, then we can say it's in second normal form. So coming to the first functional dependency, that is A determine B. A is already a candidate key and the proper subset of candidate key is pi. So we can say that there is no partial dependency as A is not a proper subset of candidate key and B is non-prime. So false and true gives us false. There is no partial dependency. Now coming to B determine C. So B is not a proper subset of candidate key, and coming to C, so C is also a non-prime attribute. So LHS must be a proper subset of candidate key and RHS should be a non-prime attribute. So this is true but this is false. So false and true gives us false. So coming to the third functional dependency, C is not a proper subset of candidate key. So we can say LHS is not a proper subset of candidate key. D is non-prime attribute. So this is false and this is true. So false and true gives us false. So this one is also not having any partial dependency. So we can say that the given relation is in second normal form. Now let's check for the third normal form. So for third normal form, there shouldn't be any transitive dependency. That is, LHS must be a candidate key or RHS must be a prime attribute. This should be true. So let's check. So first is LHS. Is LHS a candidate key? Yes. So we can say there is no transitive dependency as LHS is a candidate key. And this is an OR, so this is true. So we don't need to check for this. Now coming to this functional dependency, is LHS a candidate key? No. So we have to check if RHS is a prime attribute. Is RHS a prime attribute? No. So we can say there is a transitive dependency as LHS is also not a candidate key and RHS is non-prime attribute. Now coming to this particular dependency, is LHS a candidate key? No. Is RHS a prime attribute? No. So we can say there is a transitive dependency here as well. Now we have found out that there are two transitive dependencies which are present in two functional dependency. So we have to decompose this table. So we have to decompose this table ABCD into three tables because here we can see that there are two functional dependency in which there is a transitive dependency. So one would be divided in such a way that there is BC and one would be divided in such a way that there is CD and the rest would be left here. So that is A determine B. So it will be divided into AB, BC and CD. So now the relation is divided into three, AB, BC, CD, where BC and CD were having some transitive dependency before decomposition and AB was not having any transitive dependency. Now the table is divided into three relations, that is R1, R2 and R3. Now again we have to check for the third normal form. So coming to this relation, this was already in third normal form, so we don't need to check because A determine me was not having any transitive dependency. So coming to this relation where we have BC, where B is determining C. So we can say that for this particular relation, B is acting as a candidate key as B is determining C. So now B is candidate key and according to third normal form, LHS must be a candidate key. So we can say that now there is no transitive dependency. Coming to this table, that is CD. Now in this particular table, C determines C is the functional dependency and now C is determining D. So we can say that C is acting as a candidate key. So we can say now candidate key is present in LHS, so there is no transitive dependency. So after decomposition, the transitive dependency is removed. Now we have to check for BCNF. But now since the table is decomposed into three tables, so we have to check for three of them individually. So let's check for the relation 1, that is AB. So A will determine B and A is the candidate key here. So since A is the candidate key or super key, so R1 is in BCNF. Now coming to the second relation, that is BC, where B is acting as a candidate key and the functional dependency is B determines C. So since B is a candidate key or super key, so R2 is in BCNF because according to BCNF, LHS must be a candidate key or super key. Now coming to third relation, CD, where C determines D is a functional dependency and C is acting as a candidate key. So we can say that this one is also in BCNF. So now all decomposed relations R1, R2, R3 are in BCNF. So in this way we normalize a relation or a table. We generally decompose the table or relation whenever we find out that it's not following a certain normal form. Now consider that if you are given two functional dependency set A, or you can say relation A is having some functional dependency, relation B is also having some functional dependency, and we have to check the functional dependency which is of relation A and relation B are equivalent or not, or have a equivalence relationship or not. So for that we use the concept of equivalence of functional dependency. So what is functional dependency? A functional dependency X determines Y, where X is the determinant and Y is the dependent and Y is determined by X, holds on a relation R if for any two tuples T1 and T2 in R. So consider there is a relation R which is having some rows, or you can say tuple, which is T1 and T2. So consider if there is any attribute X and if T1 of X is equal to T2 of X, then for any attribute Y, T1 of Y would be equal to T2 of Y. So according to the functional dependency, it basically helps us to know the dependencies among different attributes of a table, what is the determinant, what is the dependent, how it is getting determined, and much more things. Now coming to the equivalence of functional dependency. So when we can say that two functional dependency set are equivalent. So two set of functional dependency, consider first set is F, second set is G, are equivalent if the following conditions hold. So the first condition is F implies G. Basically it means F covers G. So every functional dependency in G can be derived from F. So consider if there are two functional dependency of F and G, and there is a functional dependency in F that can be derived in G, then we say that this is equivalent. And same implies with G as well. So G implies F. Every functional dependency in F can be derived from G. So every functional dependency in F can also be derived by G. Then we can say that these two relations are equivalent. So if both conditions are true, then we say that F and G are equivalent. So consider there are two relations F and G which is having some functional dependency. Consider here it is A determine B and here it is B determine A. So in the equivalence we check that if this particular functional dependency and this particular functional dependency are equivalent among each other. So for that first we will see that if F can cover G, then we will see that if G can cover F, and if both of them holds true, then we can say it's equivalent. We will understand more from the example. So these are the steps on how we can find if two functional dependencies are equivalent or not. So the step one is we have to compute the closure of both of the sets. So consider if there are two sets of relation F and G. So we have to find the closure of F and G, basically all the attribute closure which is present there. Now the step 2 is we have to ensure that every functional dependency in set 1 is in set 2 closure. So consider if we have two relation F and G and we have functional dependency as A determine B and here we have the dependency as B determine A. So we'll take the closure for them. So for F closure we will have the closure of A and B, and for G closure again we will have the closure of A and B. So what is the closure of these two? So now here A closure gives us A and B, and here B closure gives us only B. Coming to this functional dependency, A closure gives us A only and B closure gives us B and A. So we have found out the closure of both of the sets. Now we have to find that every functional dependency in set 1 present in set 2 closure. So what we will do is we have to see that if this A determine B holds true for this particular equivalence relation. So what we will do is we will go to the G closure and we will see for A. A can only determine A can't determine B. So we can say that this particular relation are not equivalent. Consider if this holded true, then we have to see that every functional dependency in set 2 is having in set 1 closure. So for every functional dependency in set 2, that is A and B, we have to see this particular closure which is present in the last set, and then we have to see that if this functional dependency is holding true or not. If you are getting confused, don't get confused. We will see for this from an example. Now the step 4 is if both the subset check pass, then set 1 and set 2 are equivalent, because the set 1 functional dependency is holding true for set 2 closure and set 2 functional dependency is holding true for set 1 closure. So let's understand from an example. Consider that there are two functional dependency, one is F and one is G, and these are the functional dependency A determines B, B determines C, and in the G it is A determines C and A determine B. So we will follow the steps and then we will compute if these are equivalent or not. So the step 1 is we have to compute the closure of both the sides. So here we can see that there are 3 attributes A, B and C, and here also there are 3 attributes A, B and C. So we will find the closure of all the attributes in F. So first we will find the A closure. So A can determine B, so there will be A, B, and B can determine C, so it will be C. So A closure will be having A, B, C. Now coming to B closure, B can determine itself, so B can also determine C, so it will be B, C. Now coming to C closure, so there is nothing with C is determining, so it will only determine itself, so it will have these. Now coming to the closure of G attributes, so A closure will have A, then A can determine C, A can determine B. Now coming to B closure will be only having B because there is no B as a determinant. Coming to C closure, C can only determine itself because there is no C as a determinant. So we have found out the closure for A, B, C for all these two sets. Now we have to ensure that every functional dependency in set 1 is in set 2 closure. So consider for this functional dependency A determines B. We have to come to set 2 and we have to see that if in particular A closure do we get B or not, then we can say that this particular one is equivalent. So let's see. So in A closure we can get B, so we can say that this particular dependency holds true for the equivalence relation. Now coming to B determines C, so we have to check for the determinant, that is B, so we have to check the B closure here. So here B closure is only having B closure is not having C, so we can say that this particular functional dependency is not holding true for this case. So for now we can say that every functional dependency dependency in set 1 is not present in set 2 closure. Now let's see the reverse. So here the functional dependencies are A determine C and A determine B. The determinant here are A. So we have to check for A. Is A determining C? Yes, we can see that A is determining C. So this one is holding true. Is A determining B? Yes, we can say A is determining B. So these both are holding true. But this one is not holding true. So we can say that F and G are not equivalent because B determines C is not implied or covered by G. So what we have to do is first we have to find the closure. Then we have to do a cross. So what we have to do is, if we have to check for any functional dependency in G, we have to check for the closure of F. And if we have to check for any functional dependency in F, we have to check the closure for G, so that we can conclude that these relations are equivalent. Now, what is this minimal cover of functional dependency and why do we even need it? So, it is a simplified version of the original set of functional dependencies. It helps us to remove redundant functional dependency. So, consider if we have a functional dependency A determine B, B determines C and A determines C. So here we can see from the rule of transitivity, we can conclude that A will determine C. So do we need to have a redundant functional dependency which tell us about this? No, right? So we can remove the redundant functional dependency because from the existing functional dependency, this particular functional dependency could be derived. So it helps us to remove the redundant functional dependency. Coming to the second point, it reduces the complexity of functional dependency. So lesser the functional dependency, the complexity is also reduced. So we can say that it helps us in reducing the complexity. Third is it ensures that there are no unnecessary dependencies which can lead to anomalies in database operations such as insertion, deletion and updation. So from this functional dependency, consider A determines B. If A is a candidate key, super key, then there are very less anomalies. But if A is a non-prime attribute, then there are many anomalies which are introduced in the database. So it ensures that there is no unnecessary dependencies and the anomalies are also lesser. Now let's see that how we can find the minimal cover of a functional dependency. So step 1 is we have to decompose the functional dependency, that is RHS. If there is X determines AB, then it can be written as X determine A and X determine B, so that we can know that which all functional dependencies are redundant. So from the rule of decomposition, we have learned that if in RHS there are two set of attributes or a combination of attributes, that can be decomposed in a way X determine A and then X determine B. But it doesn't happens with the LHS because LHS is a part of candidate key or key which determines this particular attribute. Dependent can be broken down, but determinant can't be broken because that combination is determining this particular dependent. So we can broke the dependent. So here A and B is broken into X determine A and X determine B. Now coming to step 2, so we have to remove the redundant functional dependency. Now how we will find that which functional dependency is redundant? So first is make a new functional dependency set excluding the one you feel is redundant. So consider if there are 3 functional dependencies which are present, A, B and C. For now you can consider this or you can consider this as well. A determine B, B determine C and C determine D. So what we will do is consider right now I am feeling that this particular functional dependency is redundant. So what I'll do is I'll make a new functional dependency set which will be having only B determine C and C determine D. Now second step, I'll find the closure of LHS from the rest of the functional dependency and see if it determines all the attributes of table. So what I'll do is I'll find the attribute closure of this particular LHS A closure and then I'll see if this is getting determined from these particular functional dependency which is existing. If this happens, then we can exclude this functional dependency. If this A closure does not have the attribute which is getting determined, then we can say that this one is not redundant. So if yes, you can remove that. If no, then jump to the next one. So now we can go to B determine C. We can make a new functional set which is having A determine B and C determine D, and then we can take the closure of B and we can see that if from these two functional dependency B is determining C or not. If it is happening, then we can exclude this. If it is not happening, then we have to include this. Now the step 3 is we have to remove the unnecessary attributes from LHS. So earlier we removed the unnecessary attribute, or you can say we have decomposed the attributes of RHS. Now we have to also remove the unnecessary attributes from LHS. Consider if there is AB determining X. So we have to see that if any of the attribute is unnecessary, like this alone can determine all the attributes in the functional dependency, so this could be ignored. If this alone can determine all the attributes in the given functional dependency set, then this could be ignored. So we have to see that if the determinant is a super key, it can be reduced to a candidate key. So consider if AB is a super key, so candidate key is basically a minimal version of super key. So we have to see that if this version of super key can be minimal, and we can get the candidate key. So we can see that if B alone can determine all the attribute, or if A alone can determine all the attribute, and then we can remove this. So candidate key is basically a minimal super key. So let's understand from an example. So consider we have to find the minimal cover of the functional dependency A determines BC, B determines C, A determines B, AB determines C. So let's follow the step. So the step 1 is we have to decompose the functional dependency RHS. Basically we have to decompose the dependent, where if X is determining AB, we can write it as X determine A and X determine B. So let's see if there is any combination which is present in the RHS. So yes, here we can see that A is determining B, C. So we can write it as A determine B, A determine C. Now coming to here, so RHS is not having 2 attributes, so we can skip this. Coming to here, dependent is not having 2 attributes, we can skip this. Coming here, there are 2 attributes or combination of attribute, but it is present in LHS, and we have to see for RHS. So RHS, there is single attribute. So now the functional dependency set would be A determine B, A determine C, B determine C, A determine B, and AB determine C. But here you can see that A determine B is occurring twice. So we can remove that as well, because this is just a duplicate functional dependency. So the final one will be A determine B, A determine C, B determine C, and AB determine C. So the step 2 is we have to remove the redundant functional dependency. For this we have to make a new functional dependency set excluding the one you feel is redundant. So we'll go one by one. First we feel that A determine B is redundant. So I'll write it A determine B, for now we are thinking is redundant. So we'll make a functional dependency which would be excluding this. So if I exclude this, I'll be left with A determine C, B determine C, and AB determine C. This is my new functional dependency set. Now we have to find the closure of LHS from the rest of the functional dependency and see if determines all the attributes of table. If yes, you can remove that. If no, jump to the next one. So first we will find the closure for this LHS, that is A. So A closure here will give me A determines C, so C will be there and nothing else. A can determine itself. So A closure is giving me A and C. But since A closure does not have all the attributes, we shouldn't discard this. Since A closure is not giving me all the attributes, we shouldn't discard this, because right now it's not identifying all the attributes. Now we are considering A determines C is the redundant one. So we will have this A determines C. So the new functional dependency set would be A determine B, B determines C, and AB determines C. Now we have to find the closure for the LHS, that is A determines C. So A closure. Now here A will be giving me A will be giving me B, and B will be giving me C. So now A closure is determining all the attributes which is present in the table. So A determines C can also be determined from A determine B and B determine C. So since A closure is having all the attributes, and we can discard this. So we will be discarding this from the final functional dependency set. So now we are left with only A determine B, B determine C, and AB determine C. Now coming to third, B determines C. So now for B determines C, since we have discarded this, we will be only having 2 functional dependency, A determine B and AB determine C. So A determine B, AB determine C. Now we'll take the closure of the LHS for the functional dependency which we are discarding. So B closure will be having only B. So since B closure does not have all the attributes, we shouldn't discard this. If B closure would be having all the attributes, then it would definitely define C. But since it is not having all the attributes, this particular dependency can't be discarded. So we will not discard this. Coming to the final functional dependency, that is AB determines C. So for AB determines C, we will discard this, and we will have new functional dependency set as A determine B and B determine C. So A determine B, B determine C we are having. So we'll take the closure of LHS, that is AB, and AB closure gives me A, B, and B will give me C. So since AB closure is having all the attributes, we can discard this as well. So we will discard this also from the final result. So from the final result, we can say A determine B and B determine C is the minimal cover for this particular functional dependency. So in this way, we find the minimal cover. So here you can see that we don't need to go to step 3, because we have to remove unnecessary attributes from LHS, but in LHS there is only one attribute. So we don't need to go for step 3 where we are removing unnecessary attribute. This was all all about minimal cover of functional dependency in this particular video. I hope you like this video. So if you like this video, please hit the like button. If you're someone who is new to my channel, can go ahead and watch out the tech content first. And if you find it useful, can go ahead and subscribe. Also, if you have not followed me on my social media handles, you can go ahead and follow. The links are in the description. Till then, take care, keep learning, keep growing, keep smiling. Bye all.